Predicted paper 2 for AQA, everybody. If you're doing OCR, click up here because this isn't going to be relevant. If you're doing AQA, stay on here. If you're new to the channel, we've been testing out a theory to see if we can predict what questions are going to come up. What I've done is I've looked at the 2023 and 2024 papers and looked at the topics which frequently appear. For paper 2, AQA, it seems to be communication and network comes up quite a lot. Databases, talking about normalization, assembly language, and Boolean algebra. So this should give you an idea of what to revise. Also, we've looked at topics which haven't come up every single year, and it seems to be that legal and ethical hasn't come up as often, and also CPUs. The rest of the video, I'm going to be putting loads and loads of content there so that you've got plenty to revise from. However, if you do want to take your learning a step further, we are going to be holding a AQA Masterclass like we did last week, just before paper 1, and it's going to be 7:30 till 8:30 Monday night, so that you're nice and ready for the exam come Wednesday. We're also going to be including access to the online course, which has loads of exam questions on there, and I'm going to send you some resources so that you can revise outside of the masterclass session. I'll include a link in the description if you want to find out more information. However, you don't need to do that, and if you just want to get the free stuff, please at least just give us a like and subscribe just to help us grow the channel. Anyway, let's get on with the content. So in this longer style question, what we've got to do is we've got to outline essentially the fetch, decode, execute cycle, how machine code instructions are used, and talk about any hardware that we could essentially put in there. So I'm going to try and give to improve the system. I'm going to talk to you about a strategy because it says you should include a description of what happens during the fetch execute cycle. So the way that I would do it is normally these topics are completely random in terms of the 12 markers. And it's just a way to essentially say, show off your understanding of a topic in more elaborate detail. So just say everything that you can think of. Big recommendation though is 12 marks. Roughly, you're going to have about 12 to 15 minutes on this topic. This question, sorry, I should say, not topic. But the thing that I want to make sure that you're doing is don't spend too long on this and then miss half of the paper because you were spent too long on this. Give yourself 15 minutes maximum on this and then go on to the rest of the paper. Then if you've got still more stuff to add, you will have time at the end. What I don't want to happen is then you miss out half of the paper because you were doing this. If you get 12 on this, but then you don't do half the paper because you spent too long on this, that is a bad time trade in terms of the amount of marks that you can get. So that's a top tip. Do as much as you can in 15 minutes. Come back to it at the end when you've got time, because you've got 2.5 hours. So you'll probably have some time at the end to come back and do this, but don't spend too long on this. So anyway, we just need to start outlining everything that we know, because it's pretty much just says like describe. So we're just going to go through each stage. So I'd be outlining it like the fetch stage. So I'm going to show off my knowledge of the what's going on with the memory, the registers essentially. Okay, so the fetch stage, the program counter holds the address of the next instruction. This is passed to the MAR. Okay, notice how I said I haven't given any inference that the program counter has essentially the program counter hasn't passed it. I've just said it was passed, and you're probably thinking that is a really weird distinction to make. The reason for that is because when I was marking for one exam board, I remember that we couldn't award marks based on whether the student had inferred that the registers had done some of the passing, because they are just stores. So this has always really freaked me out when I'm teaching students, because I'm just like, that minute detail literally is the difference between, on one exam board, whether you were to get 1 or 2 marks, any marks actually on it. So be really clear in your wording. That's the one message that I want you to take out from all of this, is just like be super specific. It took me a really long time to learn about how to be so particular in my wording, to make sure that I'm not just being like, yeah, that's just okay. AQA are quite good, in my opinion. They are really, really good because they give you lots of points, and they give you actually quite a lot of leeway in the answers. They give you lots of different answers that you can use, but still don't risk it. The address in the MAR is is then used to fetch data / instructions from a place in RAM. This is then stored in the MDR. The contents of this is then copied to the CIR. They do sometimes talk about the memory, the memory buffer register in AQA as well. So yeah, if you use that as a terminology as well, that's absolutely fine. This is then copied to the CIR. The program counter is then incremented, which just means it goes up by one. Now what I'm going to talk about is the decode stage. So in the decode stage, the control unit decodes the instruction, and I'm going to talk about this. So this is where we bring in about the machine code instruction into opcode and operand to work out what the machine instruction is asking the computer to do. The execute stage will be the ALU carrying out the instruction and the content being stored CPU. So I don't know why I said CPU then, the accumulator. So that's all of that part there done. If you, depending on your knowledge of the assembly language as well, you may want to talk about how branching decisions are then made based on what's in the ACC. Okay, so I've kind of outlined everything in there. Let's bring that over there now. So that's outlined everything in the fetch stage. So I've shown off my knowledge. Now the second part that they've asked us to do is to talk about the hardware that can be improved in the computer system. Okay, so we've gone through all of that. Now I'll probably be making a minimum of 2 hardware recommendations that I could go up. If you can do 3, even better. We've gone through a lot of different features there, so that has given us all of the different points that we need to go through. So hardware that could, if I bring that over here actually, could be improved, could be the number of cores could be increased through using a CPU that is going to have more cores. This can allow for parallel processing, such as pipelining, where one core is fetching, the other core decoding, the other executing, which greatly increases the speed of the CPU. So we've talked about multiple cores and what we could do there. There's so many different things that you can say on this. The next one I'm going to say is increasing the clock speed. So buying a CPU with increased clock speed. You could also do cache. You could do solid state. You could do. There's so many different, like, you know, changing the hard drive to a solid state drive. There's so many different things. Increasing RAM to improve the performance of all of it. So I'm just going to talk about hardware. The next piece, or so another improvement, maybe I'll make a bit more sense. Another piece another improvement we could make is getting another improvement we could make is getting a CPU with a higher clock speed. Clock speed is the amount of FDE cycles that can be carried out per second. So if this is higher, the computer can carry out more instructions per second. Okay. So what we're going to do now is we're going to have a look at these ones, which is to do with assembly language questions. So it says normally what they do is they give you, well, they always give you a sheet with the different instructions and what happens in those. A little thing as well in the group classes, we go through this quite a lot with the assembly language because it is quite a tricky topic, this one. But as I said, they do give us these. So let's have a look. It says these questions use the AQA assembly language, which is the ARM assembly language. They can be used to perform masking, which allows, so it's just giving us a little bit of a backstory there. For example, to isolate the values in these ones, you could be ANDed to give you this. The assembly language instruction AND R0, R1, 15 performs bitwise operations and operations between the values in register 1 and number 15, storing the result in R0. So if we have a look at the result, so the result here, R0, is that's what we want to be doing there. And it's saying what is the result of this going to be. So if we look over here, it tells us that in R0, we're going to AND R1 and 15 with it, so we can see whatever's in R1 in this case here, and then we've got 15 here. And what we're going to do is we're going to AND those two together. So to AND them, it's, if we think about how the logic gate of the truth table of an AND gate, both of them have to be 1 for it to be 1 overall. So 0, 2 zeros is 0. 1 0 is 0. This one here is 0. 0. We're just looking for where the situation where we've got 2 1s. So 1, 1, 0. In binary shows the result of the application of ORR. So let's have a look at what that is. So it's going to be the OR operation. Okay. For R0, R1 48, when R1 contains the decimal value 6. So we've got 6 here in hexadecimal, 48. So this is going to be ORed. So again, if we think about the truth table for an OR gate, what's going to happen is it's when one or the other or both of them at the same time. So we put 0, 0, 1, 1, 0, 1, 1, 0. So with this question, it took a little bit of working out, but again, it's about us creating an assembly language program, and what we have to do is it's all going to be to do with, if we take the hex digits here, and then what we're going to have to do is we need to extract each nibble at that side. So if we take this as a hex digit, that on this side over here, that's 9 because 8 and 1. Then this is going to be E, which is going to be 14. So you just split them in half. And then what we need to do is we are going to get the digits here. So for the, if it's a digit, we want to put in the, so if for 9, it's 57. So there, that's 57 in binary. And if it's a character, a letter, you can see that E, which is 14, is 69. Okay, and what we want to do is we want to store these in the memory locations that they put here. So there's a number of checks that we have to do throughout this. We're going to split them in half. We're then going to, we need to check whether it's a letter or a number. If it's a letter, then what we're going to do is we're going to add on, if you look, the difference between the letters are, so 14 to 69 is 55, so we need to add on 55 to get that number. If it was A, okay, so that would be 10 plus 55, so the difference between those two is going to be 55. And then on this one here, if it's a number, what we need to do is we need to add on 48. So as you can see, 0 to 48 is just 48, and then if you go up it, all the differences between 48. So these are the checks just to run it through. We need to get the number, and we're going to split it into its separate nibbles. And then what we need to do is we're going to store them in the correct place. So it says for the the left-hand digit, we're going to store that in memory location 101. And if it's we then need to run a check is this a number or a letter? So is it above or below 10? That will then tell us whether we need to either add on 48 or 55 to it. Store that in there, and then we just need to do the same with the right hand value as well. So it's quite a tricky question, this one, and you can see that we get quite a lot of marks for this. So what we're going to do, so for the very first thing, what it wants us to do is it wants us to load the value out of memory location 100. I have put the instructions over there as well. So here we've got LDR. And then we're going to store this in register 0, and we're going to get memory location 100 out of it. Okay, it's so that's all of the things that it's asking for in the initial part of it. Now, to extract the right hand digits using the previous questions to actually help us out there, we're going to AND this, and it wants us to store this in. Well, actually, we'll store this in register 2 for the time being. So we're going to do AND. And we're going to get register 2. We're going to store it there. We're going to get what's the contents of register 0, which is just our number. So imagine it was just this number. And we're going to AND it with 15. So we put, if it's an actual value, we put a hashtag, and then we're going to put 15 there. And what that's going to be is that's going to put all ones over here. So that's going to put all ones, whilst leaving these as all zeros. So if we AND it, yeah, that takes out that right-hand nibble for us, and then allows us to actually start working with all of it. Then once we've done that, is we can then compare it to check if it's a number or a character that we're going to be using. So we use compare, CMP, and then we're going to be looking at what's stored in R2, because this is where the right-hand digit is going to be, and we're going to do this with 10, because we're checking to see, is this a number like that? So is this a number or a character? And this comes in combination where we use the branching condition, which is where we want it to jump to. So we're going to do, if it's less than, what we're going to do is we're going to put a little message, which is we're just going to be checking like it's a number or something like that. It's a number. And this is telling it where we want it to jump to. Now, once we've done that, if we jump down to where we can put this in, we might have to do some rejigging on this one, but that's okay. So we're going to go, we want it to jump to here. It's a number. And then you put like that. Okay, and then we just want to put in here what we want it to do. Now, if it's a number, remember I was saying that we want it to add 48 onto it. So we're going to do add, which is just there. We're going to store this in register 2 there. And then what we're going to do is we're going to add on 48 to it, because that's going to give us essentially the ASCII character code for it, which would be 9 in this particular circumstance. If it isn't a number, if this is false, what we want to do is we actually want to add on 55 to it. So we're going to go add R2, and then this is where we want to add on 55. So this is the circumstance. So imagine it runs that check and it's like, oh, this isn't a number, this is a character. That's what we want to do. Now here we're going to have to put in a little branch point where we actually want to check, do the left hand part of it. So we're going to go branch, jump to left or something like that, jump to left part or whatever you want to call it, it doesn't really matter. So like that, and we're going to put this down here because what's going to happen is going to, if it gets to this point, it will just start executing downwards, but we put those, which this is then going to jump from there to there if it isn't true, and it will jump through. So then we're going to put jump to left, better put that in capitals, like that. Okay, so once we've done that, and then we just need to do the same process now with the with the right hand digit. So it's, sorry, with the left hand digit. So then we put that in there like that. So that's going to be process. So it's going to be and R1, and then we're going to do, so R0, and then we're going to do, this time is essentially, we want, this is the number that we want, which is all ones under here and all zeros there, which if you do a quick calculation, 128, sorry, I know this isn't the neatest thing in the world, 32, 64, 16, okay? You add all of those together, you get 240, okay? So for this one here, we're going to run 240. That then can get those values and store them into R1, okay? And then we just do the same thing, where we're going to do a little compare. So we're going to do compare R1 to 10. If it's, we can go, it's number 2. And then this is where we would jump ahead because it is a number, and this is where we just want to put it like that. And we're going to then put add R1, store that in R1, and then this is where we're going to add 48 to it. After here, what we're going to want to do is, that's where the statement would not be true, so then we're going to do add R1, and then we do hashtag 55. Make sure you don't miss the comma out in between those two parts there. If I just move this up. And then a final part, which I nearly forgot to do, is it wants us to store the left-hand value in the 101 and the right-hand value in 102. So to do that, what we're going to do is we're just going to go to str1, which is the right hand digit. Last thing, people, is I just forgot to put the 2 in there. So that's it. Okay, so logic gates, the ones you've got to know are not, and, or, zor, nand, nor. You need to be able to draw each of these. So you need to be able, so in your notes, what I would do is I'd put a section for not gates. I'd put that the key thing with a NOT gate is that it only takes one input and then it goes into an output. So you've only got one input and then it goes into one output. This is different from the other ones, which take 2 inputs and give you 1 output. What a NOT gate essentially does is it reverses what you put in there. So if it's a 0, then the output becomes a 1. If the input is a 1, it then becomes a 0. The Boolean notation down at the bottom here, as you can see, is if you wanted to put a NOT gate, you put the letter and then you put a line above the top of it. If you want to sign up for free exam support, please click the link in the description, and remember to subscribe for more free content. We're then going to go on to an AND gate. An AND gate, way I remember what an AND gate looks like is it's kind of like the D at the end of AND, if it was all capitalized. So if you go A, N, and then you've got the D there. So with the outputs on this one, an AND gate is only true when both you have 2 1s going into it. So you've got 1 going into A, 1 going into B. And then that gives you the output of a 1 overall. The rest of them, for any other set of inputs, then that is going to give you a 0. The Boolean notation for this one is you put a dot. It's like the multiplication sign. So you just put a dot there, and that is how you would write AND in there. Or the way in which I remember to write OR is, imagine, because the back of it's curved, imagine that you would draw the O in there. You should be able to draw the O in the OR gate. So you've got it going like that. The OR gate works if one or the other or both of them together. So as you can see, the outputs are going to be 0, 1, 1, 1. And then the Boolean notation for this is just a plus sign. So one or the other or both of them is the way to remember this one. Now going into some of the gates which are you won't have seen in previous in any of the GCSE courses. The XOR gate is what's called exclusive OR. So some people call it XOR, some people call it XOR. How it works on this one, so it's the same as an OR gate. You just draw a little line at the back of it. If you miss the line out, obviously you will not get the mark for it, so make sure that you do that. And the output for this one is it's exclusively OR. So it's not when both of them together. Comparing that to the OR gate, where you've got both of them, so it's one or the other or both. This one is just one or the other. So it's, if you were to say, if you were exclusive, if you were in a relationship with someone and you're saying that you're exclusive with them, that means that you are just with them. So it means here you've got 0 or 1. So it's exclusively OR. It's not both of them at the same time. So that's the way of thinking about that one, and that's how the truth table works. The Boolean notation for this one, so it's the plus, but you just draw a circle around it. NAND is where is essentially not and. So one of the things with the NOT gate, you'll see at the start, it's got a little circle on it. Now, if you miss the little circle, you should make a note of, if you miss the circle out and you just draw the triangle, you won't get the mark in the exam. So make sure that you write that down. The NAND gate is essentially the little circle is the thing like converts it into a NOT. Think about it like that. So it's not and. Whatever and was, which is where we've only got a 1 there, a NAND gate works in this way here, so that you've just got the ones. You've got the ones for where it was 0 in the and. The Boolean notation for this one, so A and B, and then you just draw a line over the top of it, signifying that it's not. A NOR gate, which is just not OR. So again, it's exactly the same as an OR gate, but you just draw a little circle at the front of it. This essentially puts it through just knots everything. So if you imagine an OR gate, the truth table for it, 0, 1, 1, 1. This one here is going to be 1, 0, 0, 0. So it's just the reverse of it. And again, very, very similar to the NAND gate. You're going to do A or B. And then you just draw a line over the top of it to show that it's knotted. Now, a sort of knowledge question that you may get on this one is talking about the idea of a universal gate. When you come to do more complicated logic gate questions, that if you go on to study this at university potentially, there's a lot of rules which are to do with how you can change whole logic circuits into just NAND gates. And it's this idea that a NAND gate can be used to represent pretty much any other logic gate pretty much any other logic gate that exists. And it's this idea that it's what's called the universal gate. Now, you're probably thinking, why is that important? The idea that if you use just NAND gates, it can actually really minimize production costs. It can make things a lot cheaper. You can also use fewer gates, which can speed up the processing, because if you've only got to program it for just the use of NAND gates, that is actually going to make it a lot better for processing. So those are the two. If it gives you a question where it asks you to simply describe this, then you've got that in there. Some of the things as well that they may ask you to do is combine certain gates together and work out what the output for this is going to be. With the output, this is how I would do it. If it gives you this is a relatively simple one, but essentially what they might do is might give you a more complex one. When you've got the truth table, what I would recommend doing is just put a letter after each of the gates. And then all you need to do is you just need to focus on that particular gate. Where I see people making lots of errors is where what they'll do is they'll try and do too much, and they'll try and work it all out, and then they're trying to hold too much information in their head. Just split it up. So here we're just going to focus on just this one. And what we do is then we can see that this is an AND gate. So if the inputs are that, we're going to put a 0 there. If the inputs are that, we're going to put a 0 there. And then we know with an AND gate, the only way that we get a 1 is where both of the inputs are going to be 1. After that, then what we've got is then we just take on then we've got the NOT gate. So we take the output of R and we put it through the NOT gate. So 0 turns into a 1. That 0 turns into a 1, that 1, and then finally we've got a 0 at the end there. And we can actually see that is a very, very similar, where it's exactly the same output for what a NAND gate would be. Essentially, a NAND gate is a combination of an AND gate and a NOT gate, but we've just simplified it into just one gate here. Now, when you're going through this, you can obviously increase the number of inputs. You're going to get some more complicated ones in your exam papers, and it's just, as I said, just about splitting it up. That's what I would be doing, is I would be making sure that I'd be writing in what the output is here and then focusing on just this section. Once I've got that one, then I would focus on this one. And here you can see the Boolean notation where you've got A and B, and then finally the input is going to go into there. So then it's going to be plus C there, because we're going to put the C in there, and then we're going to take the R, the output of A and B, which is R, and put it through that. And on this slide here, I've got an example of that. So you write down all of the potential inputs for the 3 examples. So you go working your way through. Then we just take R. So we focus on just this section here. So if we imagine that we're just going on A and B. So what is A and B? Don't even bother looking at C, because this is just for the R column. So 0 and B is going to give us 0. The only way that it's going to be a 1 after this is if we've got a 1 and a 1. So you can see here 1 and 1. So that's why we've got a 1 there. The rest of them are zeros, because 0 and 1 for an AND gate, that's going to give us an output of a 0. And then it goes all the way through until we get right to the end, which is a 1 there. We then, once we've done that column, then what we're going to do is then we take the R column and the C column, and we're going to put it into an OR gate. So we go 0 or 0, which is 0. 1 or 0, which is 1. 0 or 0 is 0. And then 1 or 0 is going to be 1, because it's going through an OR gate, so it's 1 or the other or both of them. If we've got 2 1s, that is also going to be a 1. So that's going to be taking you through generally the basics that you need to understand for logic gates. So the 6 gates that you need to know, and how to combine certain logic gates. In the next lesson, what we'll be doing is we'll be having a look at Boolean algebra and how we can actually simplify some of these expressions to make it more easier and more efficient to look at. Would employ to trying to get you better at Boolean is, I need to teach you the 19 different rules. I know that's quite a lot. Then what I need to do is I need you to do questions, and then you can start seeing how the rules apply to the different situations. This is essentially, you're going to be using pattern recognition to do this. And you're going to start realizing that with this pattern recognition, that's going to allow you to identify common themes that come up in the question. Now, this lesson is all to do with the AQA and the Cambridge International Syllabus, because OCR use a different Boolean algebra set. So first thing, let's tick off the first step to make sure that we actually know the 19 rules. De Morgan was this person that came up with the concept of how to simplify Boolean expressions. He actually did this without computers, which is amazing. He did this in the 18th century. And what the first law is, of what we have to do is being able to switch from a not A and not B, and we can switch it over into a not A or B. Second law is not A and B. We can switch this over into not A or not B. So the first one that we need to have a look at are the different AND rules. Now, how this works, and let's talk about the logic behind these. So if we've got X, and what we have to do is we have to AND it with 0. If we actually think about the concept of an AND gate, it can only be true when both of them are 1. So even if we don't know what X is, that's a 0. So it has to be a 0 overall, because it doesn't matter what X is, because if it's a 1, it's going to be a 0. And if it's a 0, it's going to be a 0 as well. So in whatever situation, because those are the only 2 situations that can occur, that's going to be a 0 overall. If it's X here, what then's going to happen is that, and we've got a 1, it will be whatever X is. Because if X is 0, it's going to be X. If it's X is 1, it's going to be 1. So we can simplify that, get rid of the 1 there, and then that simplifies down to X. And remember that it's this whole idea of simplifying the expressions, making it more streamlined, getting less inputs in there, because that's going to make the circuit more efficient. X and X, whatever X is, if X is 1, they are both 1, so that would mean it was a 1 overall. If they are 0, it would simplify down to that. So then you've just cut down an input there. This one would simplify down to a 0 because if x is 1, not x is going to be a 0. And remember, we need both 1s to be a 1 overall. So that would be so that's going to simplify down to 0. So in any situation, if that's a 0, that's going to be a 1. If that's a 1, that's going to be a 0. So we will never create a situation where there is going to be two 1s there. For the ORs, again, when you're thinking about these ones, think about the OR gates. And how, so it's going to be one or the other or both of them. So x or 0. So that would simplify just down to x. The reason for this is because if x is 1, it's going to be a 1. If x is 0, it's going to be x. So it simplifies down to that one, so we can get rid of the 0 there. If x in this case is 1, it's going to simplify to a 1 because it doesn't matter what x is. We have got a situation where there is at least one input, which is a 1 for the OR gate. So that would simplify to a 1. X or x simplifies to x because if it's a 0, it's going to be x. If it's it's going to be a 0. If it's 1, it's going to be a 1. X or not x in this situation, because we create the situation where whatever happens, there is always going to be 1 1, and then if that's the case with the OR gate, it will simplify to a 1 because if x is 0, that's going to be a 1, so it's going to be a 1 overall. If that's a 1 and that's 0, then we've got the 1 1 there. A double not simplifies down just x, so you can take that off. If you've got more, if you've got 2 there, then that simplifies to that. More rules. With these ones here, we've got the commutative, which doesn't look like it would help out a great deal, but essentially it allows you to switch different values around. This can become more useful later on, because what will happen is if you switch things around, then you can use things like the associative rule or one of these rules here to then simplify it, but that'll become apparent a bit later on. Okay, associative is, again, it's about switching the values out. So can you see that the x is here, but if they're both ands, even though it's got brackets there, we can switch one of those in, and it may be more beneficial for us to do that. If they're both OR gates as well, you can switch them around, and that allows you to use those in these ones. One of the more higher frequency things that I see in the exam questions is the distributive rule. Now, the distributive rule works in the way of almost like expanding brackets. So the pattern you're looking for is where you've got an and on the outside of it. Almost think about that as multiply, and then you've got the or in the middle. So if imagine I expanded the brackets, that's going to give you x and y or x and z. With this one here, it's almost like expanding double brackets. So you do x times the w, so that gives you x times w. So think about it like that. Try and apply it to something that you know. And then what happens here is we've got the absorption rules, and I think probably the easiest thing to do with this one is if you have a situation where you've got two values that are the same, so one in the brackets and one out of the brackets, and you've got differing gates either side of it, so you've got a or and an and there, or an and an or, that way around. It simplifies to the one where you've got double of, so you've got two of it, so the y gets taken out of it. Don't go worry too much about it. As I said, it's probably just easier if you just go for the pattern recognition of it and just noticing that you've got the gate there and the and there. Yeah, you can spend ages trying to, actually fully understand the concepts of it. That's absolutely, that's fine. But if time is limited, I would recommend just looking at that, and the thing you're looking for is that you've got a gate that side and a differing one in the middle, and you've got two values there. You can simplify it to the one where you've got two of the values. Okay, so those are the ones there. Now, what I'm going to do is I'm going to show you some examples of the different, so actually some past paper questions. And what I would do is just, so we've ticked off step 1, essentially. So step 1 is all done. Teach you the 19 different rules. You now need to see how these can be applied to different questions. So just a quick note, the highest frequency rules that I see all the time is they seem to use the X and X. So they've got the little rules like X or not, so that they're looking for those ones, and you'll see that when we're looking at the questions. The other ones that we've got as well is that we've got the distributive rules as well. So they get the distributive rules, and then it seems to follow a very similar pattern each time. So let's have a quick look at that. Okay, so this was a question which came up, which says, using the rules of Boolean algebra, simplify the following Boolean expression. So we've got the double not rule. Now we have got the nots on the A, and then we've obviously got the B and the C. So we can take off the double knots there for those. We have to leave it on the A because obviously that's the third knot and we can't take that off. We can take it off there and off the B and the C there as well. Here we've got the absorption rule. So we've actually created in a situation where we've got the absorption rule, as you can see here. That is then given us a situation where we've got a 1 because we can apply the X or not X rule to it because we've got the not A or A. Remember, because of how OR gates work, there is always going to be a situation where we've got a 1 there because if A is 0, and that will be the 1, so then we can simplify that just down to a 1. And then we can just get rid of the 1 because we can do X, or well, in this case, it's just going to be the 1 and B or C. So then that's going to simplify down to there. I know if you're very new to this is going to feel very, very alien to you, but it's just about just keep doing questions. It's the main thing that I can say is like keep looking at the rules. Like the first day that you look at this, you're going to be thinking that this is really, really confusing. And then if you do some more questions, and you can start noticing particular patterns in there, and it's a constant battle of just more and more questions, and you will start to realize like there's certain patterns which they follow. So for example, this was another question on here. So we can see here that, so it says, apply Boolean algebra to this to show, to simplify it down to essentially this. It's saying show that this can be simplified down to that. That's what this question is saying. So you just have to do Boolean algebra on this expression here. Now we can immediately, you can start seeing the trends here. We can apply this rule to get rid of the D or not D. It's very similar to the last one in that way, so that and then we can get rid of the 1 as well. So that simplifies down to a 1. We can get rid of the 1 so that we're just left with this. Here you can see that you can use the distributive rule to essentially expand the brackets, which has given us all of these. Again, and then you can start. This is so common. You can start simplifying from this point onwards. So can you see here with where we've got things like B and B, okay? We can cut that down to just one of them because that's, in this situation, it's always going to give us that. So it's using the distributive rule and then also using essentially using the rule of then identifying the X and the other X to simplify that down to 1. And then what you've got there is then you've got the absorption rule. They've called it the redundancy theorem here, but you can then use the redundancy rule to keep cutting it down until you get to the answer. Okay, so here's 2 more questions on here as well. 2 more answers in there, so you can see here they've gone through similar sorts of steps, and then what you can do as well is then you can see. Oh, it's the same thing, expanding the brackets and then going through the identity things to be able to move through them. So it seems to be super common with that one. Expansion of brackets, use the identity rule. So can you see that these are all from separate papers and these are from different years? And what I'm trying to show you is that there's these trends that seem to come up every single time with Boolean algebra. And I think when I see my students working on this, they just don't even know where to start with them. And I would say, just learn the rules, just be able, put them around your house, write them, just be able to test yourself all the time. And then just start doing questions. I mean, even doing the same ones over and over again, just so that you can start being like, seeing if you can remember from memory, like, how is it that you actually solved the problem? And then when you start applying that to new situations, new questions, That's the thing which is going to be able to, for you to be able to start applying those patterns, those common themes to these different situations. Okay. I know that was probably quite hard, people. Thank you very much for listening. I hope that was useful. Let me know how you're getting on with it anyway, and I'll still keep putting some stuff out for you. Is essentially normal binary to denary conversions, but essentially it's just you've got a binary number in, you've got a decimal number in there. So if we go for, just put our numbers in there. So it says 4 bits for a whole number. So 8, 4, 2, 1. Now you can put fractions, or I mean here it's got a decimal, so I'm going to put that. I'm going to put a decimal point there, and then we're going to put 0.5, 0.25, 0.125, and it does say 4 bits, even though we're not going to use it, but it would be 0.0625. Okay. Now you just do your normal binary conversion, so it's going to be 1 for the 8 there. So that's 8, and then the decimal part is going to be 1, 0, 0, 0, like that, and that's how you convert it in there. Okay, if you need to do subtractions, that's absolutely fine. But yeah, that's how you do that, people. This is the other way round. So what it's saying here is, please do make sure that you read the question, because it, as you can see, it does change. So it says 3 bits for the whole number. So I'm just going to put the decimal point in there, 3 bits for the whole number. So we've got 1, 2, and 4 on that one, so that's going to be 5, and then we've got 0, so then we've got 5 bits for the exponent there, which is going to be 0.5, 0.25, and then we've got 0.125, and then 0.625, so 0.0625. Okay, so then so in AQA you have a calculator, so just add them up. For everybody else, what I'd recommend doing is, don't be afraid from doing column addition with these, because I just see so many people make mistakes on these ones. So 0, 6, 2, 5, and then just put that in like this. 5, 2, 11, 1. So that's going to be 3. Just one there. Okay. And then we just write in the number after it, so it's going to be 3, 1, 2, 5. Perfect. Okay, so that's fixed point. You just go through, it's just putting the different binary the different decimal numbers above it, which is going to be the main thing which people get wrong. And as long as you pretty much do that, you're going to be absolutely fine on those. Okay. Now the next one is 2's complement. So 2's complement is how you convert a positive numbers into negative. So let's say they want us to convert minus 68, or sorry, 68 into a negative number. First thing that you're going to do is you're just going to convert it into an 8-bit number to start with, just positive. So write all your numbers down. So that's step 1. 8, 4, 2, 1. Okay, that's step 1. Then you just convert it into a normal binary number. So that's going to be 0, 0, 0, 1. 0, so that's 68 as a positive number, and then to a negative number is going to be, we have to 2's complement it. This is my method. There are other ways of doing it, but I personally think this method is way better. You start from the right hand side and you go and find your first 1. Everything at it and before it stays the same. 1, 0, 0. Everything after it is flipped. 1, 1, 1, because they were 0, so now they become 1. Then that becomes a 0, that becomes a 1. So that's how we convert. That there is now negative 68. So just a review on that, what you do, convert it into a positive number to start with. Going from right to left, you find your first number. That is going to be, the first number that is a 1. Everything at it and before it stays the same. Everything after it is flipped. Okay, binary addition. So with this, we're also going to have a little look at binary subtraction after this. So a couple of the rules that, just as a quick reminder, is obviously 0 plus 0 equals 0. Ones, which I see people make quite a lot of different mistakes in there, is so 1 plus 1 is where it gets a little bit weird. In obviously binary, that we can't have 2. So the way that we represent that is we do 0, carry the 1, which I'll show you what that means in a second. 1 plus 1 plus 1. It's 1, carry the 1. Again, I'll show you what that means in a second. Now, I don't think... I have seen it where sometimes when you have to add 3 numbers, but this example isn't actually going to show it. But you could get a situation where you could get 4 ones. And essentially what that has to do is it has to jump over 2 spaces, okay? And I'll show you what that means and how it all fits together. But so they're going to give you this, and they're going to say to you, can you add these 2 together, okay? So it's always good practice to be able to do this, especially with later on that you have to do the binary floating point addition and subtraction, which if this isn't good, you're going to really struggle with that. So yeah, so with this one anyway, first of all, I'd probably go on the second lot here, because this is where I'm going to put my carries up at the top. So I wouldn't put like the first number there and the second number there. I'd literally just go in the middle and I'd put a number there and a number there, and then I can get all of my carries and everything all sorted. Okay, so that's step 1. And then I'm just gonna just convert the number. So 512 isn't going to go into that, so it's going to go there. 128. So I just do a quick bit of calculations there. Put a 6 there, so that's going to go, okay, 6, 4, 0, so we've got 46. It's going to be 1, take that away. That's going to leave us as 14. Okay, so, and then we're just going to go 0, and 14 is 8, 4, 2, 0. Little shortcut and 255. Because I know that for the 9th bit, that's 256, I know that it's 8 ones. So it's like if you got if you had to represent, for example, 63, it would be all of the ones here as well. So it's just a little shortcut, and it's just because I've been doing it a little while that I realized that. But so yeah, you just gotta go 1 1 1 1 1 1 1 1. Let's have a look at how we do this. So we start from the right hand side and we go 0 plus 1. 0 plus 1 follows the same rules that you know, so that's going to be a 1. Now, when it gets a little bit confusing is when you've got to do 1 plus 1. So we have a little look at our rules up here. If it helps, just write them down next to it, and you do 1 plus 1 equals 0, carry the 1. 1 plus 1 plus 1 equals 1, carry the 1. That's that rule there. 1 plus 1 plus 1 equals 1, carry the 1. We've got 2 ones there. Confusing thing because people might not have seen it where you've got 3 numbers there, but it's just treat it as this rule up here. So it's going to be 0, carry the 1. 1 plus 1 plus 1 is 1, carry the 1. 1 plus 1, so again treat that as this rule, so it's going to be 0, carry the 1. 1 plus 1 plus 1 is 1, carry the 1. Then that's going to be there. And if it did want you to put, you know, all the rest of these bits in there, you just put zeros, but we're not going to do that. Okay, so that's how you do that. Now 3 numbers, so again we're just going to convert these. So we're going to put 19, 0, 0, 0, 1, 0, 0, 1, 1. So 3, 16 is going to give us 19 there. 64 is 0. That was a bit of a weird 0. 0, 64, 0, 0, 0, 0. And then we've got 2 0, so that's 66, and then 74 is going to be 0. Then we've got 10 to make up, so that's going to be 0 0 8 0 1 0. So as you do more of these, you will get better and better at that. I'm just going to move this up just slightly, just in case you can't see it very well. Okay, right, and then we go through these. So 1 plus 0 plus 0 is 1. 1 plus 1 plus 1 is 1, carry the 1. 1 plus 0 plus 0 is 1, 1, 1, 0. 1 plus 1 is 0, carry the 1. Then finally got that there, okay? And that's how you do that with 3 numbers. Now, I did say, so let's say for argument's sake that I had a carry, and I had that, and I had 4 ones there. In this situation, what do we do? So this 4 ones equals 4, okay, and it's not going to go into this column. It's actually going to put a carry on the one over the top of it, and that's quite a difficult one that people struggle with a little bit. So you just got to remember that it is a carry, but it's just going to jump over 1, and it's going to go to that one. So that's probably the best way that I would explain that one, is it? It's going to actually jump over the column on that one there. So that's if you get 4 ones. Binary subtraction. Now this is going to use a lot of the same rules that we've actually already done. So binary subtraction essentially works with the principle that if we add a negative number, we get the same result as if we take it away. So you don't have to learn any different rules. It just has a different, has one extra step in it where you have to twos complement it. So you can see this is the reason why I've decided to teach it in this particular order, is because what you're going to do is your binary addition, I'm sure, is excellent. And all you got to do is then you've just got to, at some stage, twos complement it, which is what we did before, the second number, and then you're all good. And I've got a bit of a weird example here as well to show you so that you can sort of see how that all fits together. So anyway, we're just going to convert 65 like this, which is going to be the positive number. So that's just going to be 0, 0, 0, 0, 1. And then 43. Now, I'm not going to write this one underneath it because that's where I need to put my negative number. So what I need to do is I'm going to put it as a positive number to start with, which is going to be 0, 1, okay? And then I've got 9 more to make up there for, 11 more. That would have been a bad one. 11 more to make up there. So that's going to be 0, 1, 0, 1, 1. So that's going to be 43 there, okay? Now, once I've got that, I can twos complement it. So I use my rule, which is right to left, find your first 1, which is here. Everything at it and before it stays the same. Everything after it is flipped. So 0, 1, 0, 1, 0, 1, 1. Right? We've now got that, and we just got to put it underneath this one now. So that's going to be negative 43. 1, 0, 1, 1. Okay, and then we just use the same rules that we did on this page for this one. So then we do 1 plus 1 equals 0, carry the 1. 1, 1, 0, 1, 0, 1, 1, 0, carry the 1, 0, carry the 1. And how this works, people, is this is actually, so as you can see, the number has become smaller if we forget about this one. And what's actually happened is something called an overflow error. So an overflow error is where we actually run out of memory, and this bit gets what's called truncated and just forgotten about. So it's kind of just one of those that somebody worked this rule out, and it actually means that binary addition and subtraction works perfectly in this case. So it will give us the correct number, and as you can see, the number has gotten smaller because there's more ones over here, which is, you know, is very interesting. You know, how that all kind of fits together, and it uses that idea of overflow to actually make it work. Just thought I'd show this weird example here and just sort of talk through it. I mean, it's relatively straightforward. Obviously, in maths, the rule is if you take away a negative number, it creates a double negative, which means you have to add it on. So just if they're being a little bit sneaky, just remember that all you're going to do is you're just going to add that 14 on there. So you just do you're just going to do 22 plus 14 because the double negative there means that you're going to get a positive number. But anyway, that's relatively straightforward. Now, going on to floating point. So there's 4 things that I need to show you about how to convert a floating point number into binary. Floating point is essentially has 4 different situations that can occur. A positive mantissa, positive exponent. A positive mantissa, negative exponent. Negative mantissa, positive exponent. And negative mantissa, negative exponent. And what that means is floating point is essentially the idea in standard form in maths where you've got like 3.4 times 10 to the 4. Okay, it's just a more succinct way of representing the data. If you had a massive number with this, it's actually going to save you loads of space on a computer because you can have, you know, infinitely large numbers on there. And if you can represent really, really big numbers and save a load of space, hardware is only has its limitations. That's going to be great. So that's what the idea of floating point is actually doing, is it's trying to save a space for representing really, really big or really, really small numbers. So the method on this, and I might run out of space on this, but we'll give it a go. is the idea is the exponent, this part tells us where we're going to move the decimal point to, and this one over here is going to tell, and this one is actually the number. Now, for positive mantisses, they will always be 0, 1. Negative mantisses will always be 1, 0. I have seen questions with the exponent where don't necessarily, so 0, it will always be 0, 1 for a positive exponent, but it can actually be 1, 1 as well on some of the exam questions that I've seen. So just look out for that. If there's a 1 at the front of the exponent, you have got to do some 2's complementing. I will show you how that all works. So how does this work then? So the exponent, so step 1 is convert the exponent. So we're just going to put 1, 2, 4. I could put that there, but it's irrelevant. 6. So that tells us that we're actually going to be moving the decimal point 6 places. Okay, the number's got to get bigger. So we're going to go 1, 2, 3, 4, 5, 6. Put a little decimal point there, and then I'm going to redraw my number just so that I can remember where everything is. So 0, 1, 0, 1, 1, 1. Then I just put the numbers over the top of it. So the decimal points here, so that's going to be 1, 2, 4, 8, 16, 32. And that's going to be 0.5. So 32 plus 16 is 48. 48 plus the 8 is 56. And then plus the 2 is 58. And then we've got 0.5 there. So let's just add that on there. So that number there is going to be 56.5. Sorry, 58.5. I do apologize. So yeah, 58.5 there. Okay, so that's how you do floating point mantissa. Just going through those steps again. Exponent tells you how many times you're going to move the decimal point. The mantissa tells you the number on this. So the actual what the number is. So you work out the exponent, you move it, and then what you do is then you and then just convert the number in normal fixed point binary, which we did before. So as you can see why I've taught it in this particular order, and that gave us 58.6 in there. So that gives us all of that. Now I'm actually just going to take this out because I need more space for this one. So floating point, so positive mantis and negative exponent. You can see here I've got a negative exponent because I've got a 1 at the front. So step 1 that I need to do is I actually need to 2's complement this. So find my first 1, everything at it, and before it stays the same, everything after it is flipped. 0, 0, 0. That then gives me a negative 1. Okay, with the negative 1, what that's going to tell me is that I have actually got to make this number smaller. Okay, so before I can move the decimal point, I have to move it to the left, but to do that I need to actually put an extra 0 in there. What I'm going to do is I'm going to move that over to here, and I'm going to do 0.01. Yeah, so you put in the number of zeros for the exponent. So if I had a negative 3, I would put 3 zeros there, and so on. Negative 4, I put 4 zeros, and then I just redraw my number. So 0 decimal point 0 1 1 1. Like that. I could put in the rest of the zeros, but they're not going to have any bearing over my actual answer. And then just write the numbers in there. So that's going to be 0.5. I'm going to show you how to do it with a fraction, actually, because I personally find it easier with the fractions. But you know, if you find the decimals easier, you know, use the decimals. There's no problem in doing that. It's just personal preference, and it's still correct either way. So put the fractions in like that. So half, quarter, eighth, 16th. So to add that, in here, you know, so what we're going to do is we're going to times this by 2, because to add fractions together, the denominators both have to be the same. So then that gives me 2 over 8 plus 1 over 8, which that's going to give me 3 over 8. Okay, and then final thing that we've got to do is we're going to times that by 2, which that's then going to give us for the 16 on the end there, so that's going to give us 6 over 16. Then we're going to add the 1 over 16, which then that gives us 7 over 16. Okay, so that's our answer there. So personally for me, I find it easier to use fractions, but that's it's personal preference. If you prefer using decimals, use the decimals, that's fine. So okay, so in those ones there, what we're going to do now is we're going to go for the negative mantissa positive exponent. So I'll move this one up a little bit. And what we do is we go for the, so what we do is we can see that we've got a negative mantissa, which is where this one here is, it's got a 1 0 there. So what we do is we it doesn't really matter which order that you do this in, but 2's complement the exponent, which is 4. That tells us that we have to move it 4 places to the right. The number is going to get larger, and then what we then need to do is 2's complement this before we start moving the exponent. So that's the decimal point, which is where I see a lot of people go wrong on this one. So that's going to be 1 0 0 0. So right to left, find your first one, everything at it and before it stays the same, everything after it's flipped, 1 1 1 0. And then what we're going to do is we're going to move to the right. So we're going to go 1 2 3 4. Then so the decimal point is going to go here, which then that's going to go 0 1 1 1. And then we have got a 1 right at the end there, so we just do need to take into account about that. So it's like that. Okay. So that is going to be 1 2 4 8. So that's going to be 14. And again, you can just put the fraction here. So that's going to be half, a quarter, and an eighth. So 14 and an eighth. Now, mistake where everybody always makes on this one, they forget to put the minus in there. If you forget to put the minus, you do lose a mark on this one. So be super, super careful, people. If it's a negative mantissa, it's a negative number. That's what it's telling you. So just be careful on that one there. Okay. Final one is negative negative. So negative negative is where you've got a negative mantissa and a negative exponent. So what this one is where you have to 2's complement both of them. So what we're going to do is we're going to go to here, 0 1, everything at it and before it stays the same, everything after it is flipped. So so here is going to be 0 and 0, and then that's going to give us negative 2. Now what we would do before we added so we would 2's complement this first, and then we're going to add the zeros in. So I go right to left, so it goes to this one, everything at it and before it stays the same, 0 0 1, and then everything after it is flipped, 1 1 0, decimal point in there. Now this is telling us that this is going to get so we need to move it 2 places. So we're going to go 0 0, and then we're going to go 1 2, and then that redraw our numbers. So it's going to be 0 0, and then we're going to get a very, very small number on this one. So that is going to be so just double check I did that correctly, because that's 0. Yeah, no, it is. So that's going to be 1 2. Yep. So here, now what we have to do, I'm going to use my fraction. So half, quarter, eighth, 16th, 32. Okay. So they're adding so times that by 2, that's going to give me 2 for 16 plus 1 over 16, which that then gives me 3 over 16. 3 over 16. And then I need to times that by 2, so then that's going to give me 6 over 32, so I can add it to the 1 over 32, which is going to give me that. Now, mistake which everyone makes, forgets to put the minus in. So negative mantissa, it's just a very, very small negative number, which is minus 7 over 32. Couple of little, that's in a bit of a weird format. Just a couple of little sort of 1 2 markers that they seem to like to put in. That's a bit easier to read. There you go. That they like to ask. So for this question up here, it's what happens when you increase the precision of a number, and what happens when you increase the exponent of a number. So if you increase the mantissa, the number of bits, or decrease them, vice versa, increase the exponent, decrease the exponent, what happens to the number? The mantissa is where so what happens is you increase the precision. It just means that the number can be more precise, and like you can be more specific with the number that you're trying to represent. So that the key word that they're looking for there is that the precision is increased, and the inverse is also true. If you decrease it, then the precision decreases. the exponent is there's a greater number of numbers that you can actually represent if you increase it, and then the inverse is also true. With this, overflow can also happen is the number is too large to be represented with the number of bits that you have available. Underflow is too small to be represented with the number of bits available. Is probably, I'm actually going to change that with number of bits available. So I'm just going to slightly change that one there for you, because I personally think that's a bit of a better sentence there. There you go. Number of bits. Oh, number of bits available. So there you go. There you go. Sorted. Last bit, people. Last bit. Oh, actually, I think we've still got a little bit more actually. So, well, we'll keep going. Okay, so normalization. Normalization is the idea of essentially if we have a number here is 0.34, okay, times 10 to the 3. What happens here is this number isn't actually normalized until it becomes this. So because I've moved the decimal point to here, I actually need to make this one smaller, which is that's going to be times 10 to the 2, okay? And it's the same principle as in normalization. Positive numbers have to be 0.1, and this one over here needs to be 1.0 because there's ones at the front. If it's positive, it needs to be that. If it's negative, it needs to be this. So in this case, what we're going to do is we need to see how many times we need to move the decimal point. So remember, positive needs to be 0, 1. So I'm going to go find my first 0, 1, 1, 2. So then that's going to be 0, decimal point, 1, 0, 1, 1, 0. Add in the zeros that you need there. Now I've moved it 2 places, so I need to subtract 2 away from my exponent because I've made the mantissa bigger. So I need to make I need to counteract that with the exponent and make that smaller. So that's 3. So I subtract 2 from that. So then that is going to be 0, 0, 1. So move the decimal point. Then once you've moved it that number of times, what you then do is then you subtract it from the number, the exponent. For this one, we have to look for 1, 0. So the first time we've got 1, 0, which is there. So again, same principle. 1, 2, 3. Okay, that's great. And then we're going to go 1, 1, 0, 0, 0, 0. So just add in zeros for the rest of it. And then we had to move that 1, 2, 3. So we moved that 3 times. So then that's going to be there. Take away 3. So it's going to be 0. That's 6. So now this will equals 3. So again, just make sure, because it's a negative number, it needs to be 1, 0. And then that's going to become 0, 0, 1, 1. Tying this all together, we have to be able to convert between denary numbers and floating point as well, so go in the other direction. So first things first, what you need to do is you just need to convert it into a normal 8-bit number. Now we have got a decimal number in here, so I'm going to put 64 here, and then I'm going to go 32, 16, 8, 4, 2, 1, and then 0.5. Okay, and then I just convert 45 like so. So I'm going to go 0, 1. I've got 13 to make up there, so that's going to be 0, 1, and then it's going to be 1, 0, 1. So that's 45, and then the 0.5 is going to just be there. Decimal point is here. So that's the first stage, is just convert it into fixed point binary. The last stage is where we are actually going to move it. We have to essentially, normalize it like we were doing on the other ones, but this tells us what the exponent is going to be. So I need to move it so that it's on where it's 0, 1, and it's got to be the furthest 0, 1 on the left hand side. So we're going to go 1, 2, 3, 4, 5, 6. So we move that 6 times. Just put a little decimal point in there to help you remember. 1, 0, 1, 1, 6 times, and then our exponent is going to be 0, 1, 1, 0, because 1, 2, 4. Yeah, so on there, so 8 bits, 1, 2, 3, 4, 5, 6, 7, 8 for our mantissa, and 4 bits for an exponent. 1, 2, 3, 4. Okay, and that's the answer there. Okay, so that's how we do that. converting a negative number into floating point. So we just have to go through a couple of stages on this one. It's just an extra step. Once you've converted it into fixed point, you just need to convert it into, you just need to 2's complement it, and then just make sure that the decimal point goes between the 1 and the 0 there. So the on this one here, we're going to go for, so we'll go for 64, 64, 32, 16, 8, 4, 2, 1, and then we're going to do 0.5. Okay, so then we're just going to put our numbers in like so. So we're going to go for 14, which is going to be 0, 0, 0, 1, 1, 1, 0, and then we'll put in a 1 there. Okay, so with this one here, what I'm actually going to suggest is, instead of us having a load of leading, actually no, that is correct. So yeah, we'll go with that. And then what we need to do from this point is we're going to actually 2's complement it because it's a negative number. So what I'm going to do is I'm going to go right to left, find my first 1 and everything at it before it stays the same. Everything after it is flipped. So 1, 0, 0, 0, 1, 1, 1. Once we've got that, then so the big thing to remember on converting a negative number is that it needs to go in between the 1 and the 0. So on the left hand side. So it's going to be this position here. So I'm going to move it. So I'm going to go 1, 2, 3, 4. I can actually forget about these ones. So I'm going to put 1, 0. So I'm just going to go from here. 0, 0, 1, 1. And if it wants it as an 8-bit number, I need to just, so that's then going to be 2 more bits there. And then I moved it 1, 2, 3, 4. So the exponent needs to be 4. So that's going to be like that. So that's 4 because 1, 2, 4. And then this one up here is then going to be a negative. That's then converted into a negative number and ready to be converted back at some point. So on this way, von Neumann architecture. The A-level definition for this is a CPU that has 1 bus and 1 memory location for data and instruction. That's the first point. So it's just that they're stored in one place. It also has a control unit, and an ALU is another point. It fetches, decodes, and executes instructions from RAM. So there's probably a little bit more than what you need there, people, but those are the points that I would use. Harvard architecture is where you've got a processor that has separate storage spaces and buses for data and instruction. So data uses its own individual bus. Instructions has its own individual bus, and they all have their own memory locations. Because of the sort of application points now, so Harvard architecture is normally used for quite high processing embedded systems. The reason for this is it's actually quite a complicated program, a complicated system to work. So they need to do it with simpler tasks, but it does allow for essentially you don't suffer from bottlenecks that you would get in von Neumann because you have got the 2 separate buses. So those are some application points that you can use there. Purposes of individual components of the CPU. ALU performs mathematical operations. Everyone remembers that because of arithmetic, but then they also forget to put in the logic gates. That's how you get the second mark. Control unit does the decoding and executing part of the FDE cycle, sends control signals to other parts of the CPU. Cache stores frequently used instructions so that you don't have to go to RAM to fetch it. Different buses within the CPU. I have no idea why they like to know this when you're describing them. So the 3 of them, you'd get a mark for just stating them because they'll be like state and describe a bus. I've put them all there for you, so you can make a flashcard for each of those. Control bus, 1 mark. I don't know why they like to know about whether it's bidirectional or unidirectional. So data and control buses are bidirectional. Address bus is unidirectional. Control bus essentially sends out control signals to the input and output devices and main memory. Also receives data from them. The idea of that being bidirectional. Data bus, just remember that it does data and instructions. Address buses sends the addresses and retrieves them from the processor. Okay. The specific registers. Now, if they would just get you to state and describe them, the three that you need to know 1, 2, 3, 5. Sorry, I don't know why I said 3 there, but yeah, you need to know 5. The point with these is if you can just remember one sentence about these. Okay, so it's the holds the address of the next instruction to be executed, program counter. Holds the address of the current instruction being executed, memory address register. Holds the data that is currently in use by the CPU. Holds the result of any calculation done by the ALU. And then the current instruction register holds the instruction that currently being executed. Okay. I know that sounds really, really confusing, and at A level you are starting to get a bit more familiar with this stuff because I'm hoping that you've done some of the assembly code stuff. If you haven't done any assembly code stuff for whatever reason at school, I am going to show you how that all fits together. But what I've tried to do is use my knowledge of looking at the mark schemes to give you as little as possible to remember, and you still be able to grab a mark on this. At A level, they would probably be a second mark attached to this, and I'm going to show you how to get the second mark. But the way I've tried to make this more simple is, can you see for program counter it says holds the address of the next instruction to be executed, and then memory addresses holds the address of the current instruction to be executed. The definition is very similar. The only difference is one is current and the other is next. So one definition, you change one word and you still get the marks for it. Memory data register holds the data currently in use. So only word there that's changed is data. So again, 3 definitions. So, well, 3 definitions, but you only use one. Current instruction register holds the current instruction being executed. So again, you just change instruction. I've put in some the other little extra points as well in case they give you a 2-mark question in there as well. So program counter increments after the data is passed to the MAR. Second mark there. Memory address register receives address from program counter. Second mark. The accumulator is where data decisions are made from. Where branching decisions are made from. When we look at assembly language, well, this will make a little bit more sense, but you use things like BRZ, BRA, BRP. That is essentially how you create decisions happening there and loops and in assembly language. The accumulator is where that decision is made, so that's kind of a little extra point. The other one is input and output device. Input and outputs come from the accumulator. The current instruction register is it splits into operand and opcode. If they wanted a second mark for the memory data register, I would say that when it fetches the data from the CPU fetches the data from main memory and brings it back to the CPU and stores it in the MDR. I have no idea why this was such a big thing, but I remember when I was marking one of the papers, and you'll notice that I changed the way that I said that, which was all to do with these are just memory stores. We weren't allowing marks 1 year. This may have changed now, but we weren't allowing marks 1 year if there was an inference that the registers were like doing any of the passing. So can you see I haven't said the program counter passes the data to the MAR. All I'm saying there is that the data generically is passed to the MAR, and you're probably thinking that this sounds absolutely mental. Like, why am I going into so much detail on this? They are just memory stores, and the thought process behind this was the CPU is doing the passing of the data. These are just storing the data, and it sounds ridiculous now that I'm saying this sort of out loud, but we weren't allowing marks on one and then the other. I didn't make the decision, but it's just I do remember that. So just making sure that you're not saying like the program counter passes the data to the MAR, or the MDR gets the data from the RAM. It's the CPU which does that. I know that's a little sort of, if that sounded a little bit confusing, just get these definitions down. That's the most important thing. More of an A-level thing as well is the idea of the FDE cycle. So you need to know what the registers are doing at each individual stage of the FDE cycle. So it could be a fill in the blank. It could literally just be what are they doing at what are the registers doing at the fetch stage of the FDE cycle. So I've tried to list it and number it for you. Address is copied from the PC to the MAR. Again, no inference that the program counter is doing it, like that. The instruction held in the address is copied to the MDR. This will help you with some of the points on the previous one as well. Simultaneously, probably don't need the word simultaneously, make it easier for yourself, give yourself less. The contents of the program counter are incremented, less to remember, more likely to remember it. The contents of the MDR are copied to the current instruction register. So that's the fetch stage. Decode stage. Decode stage is the instruction held in the CIR is decoded. It's split into operand and opcode to determine the type of instruction. Additional data, if required, is fetched from memory. We'll get rid of the if required. I'm always trying to give you as little as possible to remember, and passed to the accumulator. Execute, control unit carries out the instruction, sending it to the ALU. Results stored in the accumulator. ACC is just an acronym, and you can use the acronyms to describe them as well. So fetch, decode, execute. Know that off by heart. State and describe a method in which the CPU performance can be improved. I've put 2 on here, and then on the next slide I've put the other 2. So clock speed is one of the first ones. You can increase the CPU speed by increasing the clock speed. The clock speed is, so if you have a 3 GHz processor, that means about 3 billion fetch, decode, execute cycles happen per second. So the higher that is, the quicker the computer is. A computer core, so number of cores, if it has more cores, generally this is going to be faster. This is because it can work on different things simultaneously. We're going to have a look at pipelining in a second and what that means. And essentially what this is if you have multiple cores, you can do something called parallel processing, which just means you can do things all at the same time. Cache is another one. So it's the same question. I'm just putting all of the points on there. Cache is essentially a little memory store in just within the CPU, and it just means that the larger that is, you don't have to go to RAM to fetch anything. So it stores frequently used instructions. So the less you have to go to RAM, it's going to shorten that space. Then it's going to simplify the whole process. Pipelining is one that you won't have heard at GCSE, but pipelining is a one which is every core is doing a different part of the fetch, decode, execute cycle. So it's this idea that one core is fetching, while the other core is decoding, and the other is executing. So, and you need to say it in that way. So one core is fetching while the other is decoding and the other is executing. And this allows for parallel processing. And all 3 of that, it's normally a 3-mark question. You get 3 marks there. Very quickly, what they might get you to do is they might just get you to calculate which is going to be the faster one and why. So you've got a gigahertz, this one over here, 1 gigahertz, and you've got 4 cores, 1.4 gigahertz, 2 cores, which is faster of why. Generally, ignore the cache. If they are the same, that could be like the tie break factor, if you get what I'm saying. So I'll explain that. 1 gigahertz is 1 gigahertz times the number of cores. So total clock speed is clock speed times the number of cores gives you total clock speed, which is 4 gigahertz. The other one is 1.4 times 2 equals 2.8 gigahertz. Comp 1 is going to be faster for the flight simulator in this case because it has a higher total clock speed. If they happen to be the same, and then you had the cache size, and that was the only deciding factor, then you might make a case and say, like, well, they've got the same total clock speed, but the cache size is the same. The cache size is different, and this one is larger. That might be the sort of tie break between the 2 of them. Embedded systems. The definition for this, if they just ask you like what an embedded system is, within a computer system within a larger system with one purpose: fridge, microwave. An embedded system, they may also say like what is an embedded system in a particular situation. I've used a car there, car parking system, GPS, automatic windows. The alternative to that is a general purpose computer, and a general purpose computer is what you're using right now, I would suspect, which can perform multiple tasks on multiple purposes, e.g. desktop computer, all that stuff. Linking that back to von Neumann and Harvard architectures, generally von Neumann is general purpose computers. Embedded systems are Harvard architecture. Okay, so we've got that one. Okay, right. So now going on to primary storage, and I think the definition is actually changed on this. So I'm just going to leave it to that. I'm going to take those two out on that one. So give an example of primary storage. It's a piece of memory that is directly connected to the CPU, which is RAM and ROM. For a while, I remember that they did use, I think it was in like maybe 2018. Anyway, you don't want a history lesson on it. Essentially, they use cache and registers, but I think they've changed that now. So I'm going to leave it out because I don't want to take any risks. We're just going to say RAM and ROM because we definitely know that. Sometimes the definitions change with what people are given marks for and stuff like that. So let's go with that and not take any chances. Secondary storage is the idea of non-volatile permanent storage for files and applications when not in use by the computer. The concept, if you just remember the definition, great, that's the kind of first step. But the understanding of this is when I want to use something, I load it from secondary storage, which is when it's almost like dormant, and then I load it into RAM. Then what happens is I'm working on it. So right now, like my PowerPoint is working on it, and essentially what with that, I'm getting the data and instructions and everything from there, and it's that idea between the two of them. ROM has some really important programs and instructions on there, which we'll talk about more in a second, but yes, generally it's the idea that you go from secondary storage when not in use. RAM, we load it into RAM and we start doing stuff on it, and then when we don't want to use it, it goes back into secondary storage. They do sometimes get you to compare the RAM and ROM. I was doing some questions with a student the other day, and did have this. RAM stores instructions and data that are currently in use by the by the computer. It also stores the operating system, which is in use by the computer. ROM stores the BIOS and bootloader. The BIOS and bootloader are some of the most important programs on the whole computer. We do not want these to be changed. We do not want these to be edited because when you turn the computer on, the bootloader is the program which essentially loads the operating system into RAM, essentially turning the computer on. So this is one of the most important programs on the whole computer, which is why ROM is read-only. RAM is read and write, which essentially just means that you can change stuff on it, which makes sense because it's the stuff that we're using in this particular moment in time. ROM is just read only. We can just read it because when we turn the computer on, that's what we want to do. What does it store? So we've kind of talked about that already on those ones. The other sort of, if they ask you to compare them, RAM is what's called volatile. When you turn the computer off, it doesn't remember anything on it. ROM is non-volatile, which is when you turn the computer off, you still want to be able to have all of the things on there, because if it forgets the BIOS and bootloader, we could never turn the computer back on again. State the purpose of ROM, kind of already done that there, but I guess that's just not putting it on a table. So I'm going to skip that. Talked about volatile and non-volatile already on the previous one, so I'm going to skip that as well. If you want to make flashcards on those, I'll just leave it up there. Leave it on there. There you go. Okay. Virtual memory. Virtual memory is it's essentially where we run out of RAM. The computer can either crash, or what can happen is it can actually use virtual memory. Virtual memory is where we use part of our hard drive and we use it as RAM because we've run out of space. Now, the idea, which I guess is probably a little bit more of a, you might want to add on there, is linking this to the operating systems unit, which unfortunately I don't think I'm going to have time to put out a lesson before paper one, so I'll tell you about it now. One of the jobs that the operating system does, so let's say that you get a question which is operating systems, and it will ask you to describe some of the jobs that the OS does. User interface, definition to use on that one is hides the complexity of the hardware from the user. And then you can, if you need to give an example, graphical user interface, command line interface. But the other one that you can talk about is memory management, and you can use and say, like, it does memory management, and it does this thing called paging, which is where it's essentially puts data into chunks And what it does is it loads these pages into so from RAM into the CPU. And these pages have to be what's called contiguous. Tying this together with virtual memory, one of the jobs of the operating system is actually to, when we run out of RAM, is to use virtual memory. And if you talk about that in there, so if you get a question where it's like, name a job of the OS, and you can go memory management, you can say, oh, it creates pages, and the other one is segmentation. And it also does the virtual memory, which is when the hard drive, when the RAM runs out of space, that it uses part of the hard drive uses part of the hard drive and as RAM. And what it does is it loads things from the hard drive into RAM so that it can be used by the CPU. Now, the advantages of this is it's virtual memory stops the computer from crashing. Big advantage. The bad thing is, though, is it's very slow, and it creates this thing called disk thrashing, which is where the whole process and everything just slows down, and it's it's just a lot slower. So that's the kind of main thing. And if you use the key term disk thrashing as well, that would give you a mark just for that as well. So that's virtual memory. Okay, secondary storage. We gave a definition for secondary storage already, but the three main types is that you've got solid state, magnetic, and optical. Now, with these, so this one is optical, and you also got to know how to describe how it works. Don't know why we still do about CDs and DVDs, because they kind of, no one really uses them that much anymore. But anyway, examples of CDs and DVDs. If it asks you about a scenario and you need to give some kind of advantages and disadvantages about this, quick advantage is CDs are portable, but the main problem is they get scratched really easily and they're easy to damage. So optical, first mark, disc spins and laser is shot at the disc. Okay, so disc spin 1 mark, laser is shot at the disc is 2nd mark. So yeah, you get those. There are these things called pits and lands, which go out a spiral from the middle, so 3rd mark. The laser reflection is measured when it passed over the pits and lands, 4th mark. It then determines whether it is a 1 or a 0 based on whether it goes over the pit or the land. So 5 marks there. If it's 4 marks, then you don't need to put as much. Hard disk drive. I always try and make it as simple as possible for you to remember. HDD has a disk which spins, so same as the CD. So HDD is an example of magnetic storage, by the way. Disk is split up into tracks and sectors. A read and write head passes over the different areas and reads whether the data is a 0 or 1. I would actually also add on there that how it does that is it has magnetized particles, and whether these particles are magnetized or not magnetized is the thing that determines whether it is a 1 or a 0. If they give you a situation where they're asking you for your recommendation of whether you would use this, I have seen this one situation where generally you use solid state in every situation, which we're going to talk about. But say if there was like a budget constraint and there was a company that maybe didn't have as much money, and it was maybe trying to do something for like backups in the evening, where speed, like even though HDDs, like they have actually quite quick write speeds, not as fast as solid state, but it's not absolutely essential that you have to do everything as fast as possible, and it's cheaper than solid state. You could use magnetic storage as a backup. So that would just be the one situation which I just thought I'd draw your attention to on that one. I think I skipped one. Yeah, okay, so solid state. Solid state works by having an electrical charge that is either trapped or not trapped by NAND gates. If it's trapped, it's a 1. If it's not trapped, it's a 0. And then this is red. So you'd always, with every single one, just make sure that you know how to describe whether it's a 1 or a 0. Examples of this is SD, USB, solid state. Advantages is portable, has the quickest read and write speeds. The only real disadvantage is that it is slightly more expensive than the others. Just in case you get a question about cloud storage. Now, weirdly, they called cloud storage, I think this was on OCR, maybe on AQA as well. They called cloud storage virtual storage for a while. I don't know whether they've changed that now. And I think they may have changed that because of the confusion with virtual memory and virtual storage. Like, they sound kind of the same thing. Yeah, so just be careful of that one, because if they kind of like in the question, they seem like they're talking about virtual storage, and it seems like they're referring to clouds, or like, you know, people working in other places. They're talking about cloud storage, so just careful on that one. Cloud storage is where the storage is not held on the actual device but in a remote server in another location. It requires an internet connection. The advantages of this, just quick ones: can access files from any device as long as you have internet, easier to collaborate with other people. Negatives though is has to have an internet connection to access it, and you are trusting a third party with the security of your files. Whilst the security, I'm sure, is very, very good, we are trusting people that they're going to be good. Couple of little input and output devices. I was having a quick look at the ones which I thought maybe were a little bit not so obvious. Barcode readers. The way it works is it reads the thickness of the line. So you've got guard bars, which are just almost like, I guess, almost like the quotation marks around a when you're writing in a print statement in Python. It's like saying, like, this is the area you're going to look at. The light shines on the barcode, and that then can measure the thickness of it, and then that turns it into a number, which will be an equivalent to, for example, in this case, a banana, and then other little extra bit that you have to put in there. That then is linked to a database which will subtract one from there and say that you have one less quantity in stock. So shine a light on there. So you shine the light, that measures the thickness of the lines, that then links to a database. The database subtracts one from there. Sometimes they sort of ask, like, how does it automatically like reorder stuff? So you would say when it gets to a certain quantity in the database of numbers in stock, it automatically reorders that from there. So I just thought about barcodes there. Digital cameras break up what it sees into a grid of pixels. The shutter opens to let light in onto the sensor at the back of the lens. The intensity of the color of the light is measured by the tiny sensors of each of the different pixels. Laser printers, they use something called toner. Don't use liquid ink. It uses an electrostatic charge to produce text and images on paper. Generally, laser printers, they use that over inkjet printers for large numbers. So that's why schools, organizations use laser printers, because if you need to do 100 copies of something, it does it really, really quickly, because it does it the whole document. For 1 or 2 copies, it's actually quicker to use an inkjet printer, which is just probably the one that, if you have a printer at home, it's got that one there. Okay, so that is going to be everything for AQA. OCR and Cambridge International, I just need to go through a bit of RISC and CISC. So, okay, so CISC processor. Now, with this one, essentially what we are going to do with this one is there's 2 different sorts of processor styles, and they are to do with the amount of instructions that they hold. So CISC processor has a really large instruction set that is used to accomplish tasks in as few lines of assembly code as possible. They're a bit simpler to use. I remember there was a question where they asked you, a company was thinking about upgrading its computer systems, and I just thought it'd be good to have a couple of advantages and disadvantages about this. Generally think of CISC as like what you're familiar with using, and in the answer it was all to do with that these people were familiar with using CISC. So the big advantages is that as a company you don't have to spend time training people on how to use RISC, which I'll talk about in a second. You don't there's not going to be a time where people are making mistakes. People are just familiar with using it. Disadvantages though is that it does have a higher power consumption than RISC, and it doesn't allow for pipelining, which we talked about is really can speed things up. So RISC, very small. It's got simple instructions, so you haven't got many an instruction set which is very large. One clock cycle can accomplish all the required operations in so it's just one clock cycle per instruction, so it's very, very fast. Advantages: it's very fast when it's using pipelining, low power consumption. People aren't super familiar with this though, so they aren't. This isn't something that they know, so that you would have to spend time. People are going to make mistakes. That's going to cost the business money. Anyway, so what I'm going to try and do is for tomorrow, I'm going to try and get a little thing about assembly language for you all. But I hope that was useful, and I wish you all the best for exams that you've got coming up. But what is a database to start off with? An organized collection of data into fields and records. A flat file database is a database that only has one table. An entity is a category of object, person, event, or thing, or of interest, which the data needs to be recorded. You would normally see a well-made database will have a table per entity. Now, in badly made databases, you actually have the entities all mixed up together, which we're going to talk about some of the problems with a flat file database where all of the entities are mixed up with each other. A relational database is where you've got more than one table connected through relationships. You would also use foreign keys and primary keys to connect those. A primary key is a unique identifier of a record in a database. Foreign key, a primary key from another table used to create a relationship between the two tables. And a secondary key. So a secondary key is very, very similar to a primary key. It uniquely identifies a record but isn't the primary key, and can be used when narrowing down a search or indexing of the data. Entity descriptions. Sometimes they ask you to do an entity description. Now, the table name. The table name is going to be displayed on the left-hand side, so like customer, product, and subscription. The entity descriptors, or the field names, so the column names, they would be displayed here. So you've got customer ID, title, first name, surname, and email. And then the other thing that you've got is you need to have the primary keys underlined. So the primary keys are what uniquely identify each of the records in there. Now, when we start talking about normalization, composite primary keys are where we join two attributes together to create a unique identifier for this. So for example, we could join together order number and order line to create what's called a composite primary key. This will become more important when we start talking about normalization and how we go from an unnormalized database into third normal form. But generally, that's what a composite primary key is where we take two identifiers and join them together to create a unique identifier. One of the questions that you could get is where it will get you to do what's called an ERD diagram, which is an entity relationship diagram. And there's three different relationships that you can get. You can get a one-to-one, a one-to-many, and a many-to-many. Generally, you will always be trying to go for either a one-to-many, or in a perfect circumstance, or you'll be going for a one-to-one. A many-to-many is generally seen as is not good, and we will be talking about why that is in a second. But things that you can do when you're trying to draw your entity relationship diagrams, a couple of little tips, is if they're giving you some databases and they've given you the different tables on there, a one-to-one would be a situation where, so the example I've given here is a car and the employees. So the employee, one employee has one car, so that they have it's a one-to-one, one employee to one car. A one-to-many might be a mother to children. So the mother has multiple children, but with the children being paired up with their mother, the mother may appear multiple times. So that's where you would get a one-to-many relationship. A many-to-many is actors and films. And normally this is displayed by a flat file database, which we'll look at in a second why a flat file database is not preferable. Referential integrity is another keyword. There are a lot of keywords in the database unit. Referential integrity means that no foreign key in one table can reference a non-existent record in a related table. That's a little bit of a confusing definition, but essentially what that means is referential integrity. If I needed to put in, let's say that I needed to put in the BMW, and we had a car database, and what happened is I accidentally missed out one of the letters in BMW. This has created an inconsistency, which then means that I no longer have referential integrity. Because I don't have referential integrity, that can cause issues when I'm trying to search. Because if I say that I need to display all cars that are BMWs, I put in my report that I need to output all of the data for this, but it's not going to pick up on the values that I've spelt BMW wrong on there. So the inconsistencies can cause problems with searching, and that's why that we need to make sure that all of the data, if we are referring to something, that they are spelt the same all the way across the database. Little example here of some of the key features on there. So customer ID, sub ID, and product ID, these are unique identifiers. These are the primary keys here. You can see that the link has been created from customer ID and customer ID here. That is where we've used the primary key, and now it has become a foreign key in the subscription table. Product ID is also going to have the foreign key here. So I just wanted to show you an example of primary keys, where you've got the foreign keys, so creating the links between the tables there. You've also got a couple of other things in here. So we've got the field. So the fields is like customer ID, title, first name. So these are the columns, and then the records, they are the rows in there. And all of that together is we've got the table, the customer table, the subscription table, and the product table. Now with this, if I was trying to represent this in an entity relationship diagram, this is actually quite important. So a lot of people don't understand where they would need to put what's called the crow's foot. So the crow's foot is when you're drawing the entity relationship, it goes on the table. Okay. Now, a little tip to knowing how to do this is the crow's foot goes on the side where there is a foreign key. So can you see on customer ID and product ID, they are foreign keys. So that is the reason why we have put the crow's foot on there. So if you have a question in your exam and it's asking you to draw an ERD diagram, you're looking at the table, and if it has a foreign key in one of the other tables, that is where you're going to draw the crow's foot onto. In a many-to-many relationship, this would be an example here where you've got multiple entities together. We've got products, which that should be in its own table. We've got customers. It's all jumbled up, and this is generally seen as quite a bad style of database because we get repetitions of data and lots of things which aren't necessarily too good. So with all of these different questions here, one of the big things that I always see is that the answer is actually the same for all of these. So disadvantages of many-to-many relationships, disadvantages of an unnormalized database, which we're going to talk about normalization in a second, and the disadvantages of flat file databases. They all have the same disadvantages, so that this can save you a bit of time by trying to remember how to actually answer these questions. So repetition of data happens in all of these, that's a big disadvantage of these. When you have repetition of data, the follow-on point to that is that it causes data integrity issues. So when I was talking about the referential integrity, because you've got repetitions of data, that then means it's more likely that you're going to make a mistake when you're trying to enter that data into the computer, which then that means that when you're trying to search and you're trying to find things in the database, you're less likely to because of those data integrity issues. Now, we mentioned normalization. Now, normalization is essentially where we're trying to make the database more and more better designed. And we go from what's called unnormalized to first normal form, second normal form, and third normal form. The question that I've seen on this one is where they'll give you a database and they will say to you that this is unnormalized. What are the steps that you have to go through to get from unnormalized to first normal form, second normal form, or third normal form? So flashcard on each of these, this is what you need to do. First normal form is it shouldn't have any repeating attributes. So I'll show you what that looks like in a second. All attributes need to be atomic. You do not want to have full name. You want to have you want to have first name and surname. So you need to make sure that the data is all split up. So in here, what we've got here is we've got repetitions of data in there. So we've got Monday, Monday. That shouldn't, so this is an unnormalized database. This is not in first normal form. So that is a situation there which we do not want to have. So what we would need to do is we would need to start creating a link table in there so that we could start removing some of these repetitions of data. So as you can see here, we've split the entities up, and this then allows us to not get those repetitions of data. So to essentially take it from unnormalized here into normalized, and you'll be explaining this in your in the question, is I will remove repetitions of data, and I will also make sure all of the data is atomic. One of the ways that I would do this is I would create a link table, so split them up into so that there's lots of different tables, and also then I would create a link table where we've got the foreign keys there. Now, second normal form is where we remove what's called no partial dependencies, which is just where some of the data is dependent upon primary keys which aren't relevant to it. And the main way that we shift it into second normal form is all you need to say is with the link table, we use the foreign key to create a unique composite primary key. So we join those two together to create a composite primary key. Generally, because it's not going to be a massive database that's going to be in your exam question, what I would say that you need to do is to get it to go into third normal form is that you can actually probably stop there, because if you've only got to split it into 3 entities and there's only 3 entities there, and you've got a link table and you've created a composite primary key, that would also actually take it into third normal form. In a certain situation, if they did ask you like, what does third normal form mean? You say all attributes are dependent on the key, the whole key, and nothing but the key. And what that means is, let's say that you still split it up, and then there was one table, so that you've got the link table, you've created the composite primary key, but one of the tables actually had the instructors on there. You just need to make sure every entity has its own table. If every entity is separate, then they cannot be dependent on the primary key of something that it shouldn't be. So that there is no, what's called is it's dependent on the key, the whole key, and nothing but the key. So it's just those attributes are dependent upon its own primary key and nothing else. That's what that means. But the general thing I want you to go with is to go from unnormalized going into. So what you're going to do is you're going to create a link table, remove repeating data attributes, make sure that everything's atomic, create that link table. With the link table, to get it to go from first normal form into second normal form, is that you then create the composite primary key. And by that, if you've gone through and explained that process, generally it should have gone into third normal form at that point. If you notice though that there is another table that you could create because you've got some instructors or whatever, that would then be how you take it from second normal form into third normal form if it isn't already there. Okay, so now we're going to move on to SQL. So SQL, the format of SQL is select from where order by. Now select is where we get the fields to be displayed. So from the database, from is the table name, where is the almost like the if statement, and then order by if you wanted to go in ascending or descending order. So this is showing you a quick example here. This table here, this is for names and breeds of female dogs. So I select name, breed. So you separate that with a comma. From dogs, so you put the table name, where gender is equal to female. And we make sure that we put that speech marks around that. Now you could put a double equal to in if statements. In SQL, just remember that you actually only put one equal sign. All of the other things are relevant though, so like greater than, equal to, less than, not equal to. That all works exactly the same, but just I thought I'd highlight that it's only one equal sign on the where statement of SQL. Now, the little star here is wildcard, which that is a shortcut for selecting everything. And then you've got from dogs where age is greater than or equal to 4. So that's that. Order by. You've got, if you need it to go in ascending order, so select star from members where num is greater than 10, order by surname. You don't need to put anything for it to go in ascending order. It will just automatically do it. But if you want it to go backwards in descending order, you need to put DESC at the end of it. So this is how you would get data from multiple tables, and you're going to use the join keyword on this one. So the join keyword, what it allows you to do is take data from multiple tables and then display it. So a couple of things which you won't be familiar with. You have to use what's called the dot notation. The dot notation is essentially where we've got like table player dot surname. So we put the table to start with, and then we have to tell it the field name that we're going to that we want. So surname, first name, team name, and table.team. Then what we do is we select both tables in this case, and then this is the join keyword. So you're going to say join table player onto table team.team ID is equal to table player.team ID. And it's really, really important here that you join it based on the primary key and the foreign key. So it's the foreign key here, that's how we're creating the relationship between the two tables. So that's the one that you're going to go for on that one, and that's where you put the after the on, and then you just simply put the information in that you want it to go for. So table team dot team name equals Binham. Now, altering a table structure. So one of the things that you need to be able to do is to add a column if you want to. So alter table is the keyword on that one. Table product, add quantity and stock integer. Is how we would add in a new column there. Deleting or altering the table structure. So to delete a column, we go alter table dot table product, drop quantity and stock. So that's going to delete a column there. To alter the table and say that we need to modify the data type on there, we're changing it into a varchar. That's going to accept essentially up to 30 values. You can put it in there like that, and you just use the modify column on there. Insert data. It's quite important on this one. So insert into, and then you put the table, put the field names, and then you just put the values. Very important that the values that you want to add in match up to the field name. So if you put A3, 4, 5, and you didn't put it in the correct data type as well, that's another thing. So if you forgot the speech marks and you put it over there, it wouldn't work. So you need to make sure it's in the correct order on those ones. Updating. What we do is you use update, set description, and whatever the things that you want to change, and then you just have to identify it normally by the primary key. So that's going to be there. Deleting a record, delete from product where product ID. So using the primary key to help you do that. Now this is just going to be relevant for the OCR specification. So the ACID principle is atomicity, consistency, isolation, and durability. So it's this idea of that we've got certain properties that are going to ensure the integrity of the database is maintained under all circumstances. And what you need to know for the exam is like what each the A, the C, I, and D all mean. So if we just go through and do those, you can just make a flashcard on each of those, remember the definitions, and then you'll be able to get some marks on those ones. So atomicity, it has to. So if we've got a transaction or we're trying to put something into a database, it has to be processed in its entirety or not at all. So let's say it crashes, you can't process part of the transaction. Consistency, that no transaction can violate any of the defined validation rules. So and this is going to help us with referential integrity. So again, just making sure that your database is consistent with all of the data that we're inputting. Isolation ensures that concurrent execution of transaction leads to the same result as if transactions were processed one after each other. So it's just going through and making sure that everything is processed and we're going to get the same result in that regard. And then also durability, so ensures that once a transaction has been committed, it will remain so even in the event of a power cut. As each part of a transaction is completed, it is held in a buffer or on a disk until all of the elements of the transaction are completed. Only then will the changes database tables be made. So once everything's finished, then it's going to process the actual changes to the database. Now, that's good. That's all we've got for today, people. So I really hope that everything goes well. I'll try my best to get the OOP lesson out for you tomorrow as well. So best of luck. Hope everything goes well, and all the best. Okay, this is the June 2023 paper for AQA, and we're going to be going through this now. So let's have a look at this one, this question here. A sound is sampled and recorded digitally. The sound is sampled at a rate of 48,000 samples per second for 3 minutes using 16-bit sample resolution. Calculate the size of the digital recording, giving your answer in megabytes. Give the answer rounded to 2 decimal places. So we do have a calculator in the exam, so the calculation that we're going to do is 48,000 times, and then we have to do it by 16 bits for the sample resolution, times 60 seconds times 3, because it's for the amount of seconds, so obviously 60, you could do it by 180, but just do it like that. And then and then once you've worked that out and everything, then with that answer, then you're going to divide it by, that will give you it in bits. Okay, so that's in bits. So you'd get a mark for doing all of that, and then to convert it into megabytes is where you get the second mark. So you convert it to bytes by dividing by 8, divide it by 1024 to give you it in kibibytes, because that would be bytes to kibibytes, and then from there it's going to be 1024 to go, because there's 1024 kibibytes in a megabyte, so then you do it like that. So you're just going to put that in on your calculator, 48,000 times 16 times 60 times 3 divided by 8 divided by 1024 divided by 1024, and it says rounded to 2 decimal places, so that would be 16.48 megabytes. The highest frequency component in a different sound is 15,000 hertz. What is the minimum sampling frequency that we should be used in the sound to ensure that all frequencies in the original waveform are preserved? Generally, what you have to do is you have to times it by 2. Okay, so then what you're going to do is you're going to times that by 2, so then that's going to give you 30,000. Next one. This shows the part playing a sound that has been sampled. The binary sound data is used to generate an electrical waveform. A hardware component on the sound carries out this process in figure 1. State the name of the component. This is the ADC, analog to digital converter. Question 2. Show some of the fields contained in a packet transmitted on a computer network. So we've got destination address, source address, payload, and checksum. State 2 other fields that are not included in there. So we've got time to live, which is to do with the hop limit, where it goes between every single router. The other one is sequence number. So it's like, say you've got 10 packets, this would be like, so it would be like the first one of 10 or the third one of 10. Explain what a checksum is used for. A checksum is used for the, is essentially used to check if there are any corrupted packets. Outline how a checksum is used. What you do is you apply a hash function to the packets, and that will generate you a value which you send over. So you just need to say hash function, because it's only, you essentially get 1 mark for the top bit, 1 mark for there. So hash function applied to packets to generate you the value you send with other data packets. Packets are transmitted using packet switching. Describe the role of the router in packet switching. So the router will forward data packets based on their IP address. Also send data packets to other routers. So put this up. on the way to the destination, this is known as a hop. So it forwards data packets based on their IP addresses, and then also what it's going to do is it's going to send it to another router, which then from that router that it sends it to potentially another router or its destination, and that's known as a hop. Also just add in there that it will it finds the most efficient route to the destination. Okay, good. So the next question is us talking about encryption, which is essentially here we've got a Caesar cipher where it moves everything along by 4. So what we've got to do is we just get the letter S and then you go T, U, V, W. This is a test of how good your alphabet is, because that I always forget it. But yeah, then you've got E, F, G, H, I, and then you just work your way through the rest of the questions like that. So then you go, and then yeah, you just go through the rest of the list, and then it's all there. Just be careful of case. The next one says state one weakness that both Caesar cipher and the cipher shown in this one here, because we've got a different one. Key thing to notice in this one, so it starts off C obviously is 2 away, D is 2 away from B, but C, that isn't the same, is it? So what we have to do is that's actually going to be a more complex cipher, that one there. But we can still work it out, obviously. So the way that we can do it is if there is enough text, someone will be able to work out the missing cipher, or the cipher, as they can go through the text and give us and work. They can work out the cipher as they go through the text and look at frequency of letters. So there's this like frequency analysis which you can do, which is every time that you get a particular letter, then you can assign it to that. The second one is harder to crack though, because as we already mentioned, is that the ciphertext is random in comparison to cipher, which is the same every time. It's the same amount of characters away each time. So and then you maybe, I mean, it's only 1 mark. If it was 2 marks, I'd say maybe give an example just to really hammer that point home. I don't know if I also said about this, make sure that you get the case there as well. Because I do think they would dock you a mark as well. So just be really careful of that one. So now we've got to talk about the Vernam cipher, which is a lot more of a secure, is a more secure encryption. So this is to do with where you use a one-time pad, which is truly, the pad is truly random. They sometimes use things like, they use all sorts of things for this, but yeah, just completely random occurrences to generate the one-time pad which you send over, and then you can apply that with the encryption. And they do it with, I believe it's a XOR gate, so they XOR it, and then that gives you the value. And then condition 2 that we said is that they can only use the one-time pad once, which is just essentially the encryption. The next question is talking about interrupts in the fetch, decode, execute cycle. Describe what an interrupt is and explain the purpose of the interrupt. So, purpose of interrupt. So, an interrupt is where a device or program requires urgent attention from the CPU. It gets it to stop what it is doing and work on the higher priority task. An example of this, if it is a hardware interrupt, such as a device has no power / printer out of paper. Okay, you've also got software ones as well, which you could say, which is divide by 0. So when you try to divide by 0, that's one of those ones where it messes the computer up. Try it on your calculator. It doesn't know what it is. It's undefined. So yeah, that confuses the computer. So stack overflow, another one in those ones there. So there's a variety of different ones that you can talk about, but it's this idea about it stopping it. Because it's a 2 marks, I don't think it's entirely necessary for us to talk about how we get the task we're working on gets pushed onto a stack. I think that's a little bit overkill. I think give a description, give an example. That's absolutely fine. Okay, we've got a database question. Now, the hard part with all of this is trying to work out actually what are the things that it wants us to put in there, because we have to do entity descriptions for the database. What we can work out is that there's 3 tables that we need. Okay, we need customer, we need maybe like a booking table, and then like a booked seat, something like that, table in there. And it's the relationship between all of those and how they're linked. So what we've got is we've got customer, and it says it wants the primary keys underlined. So what we're going to do is we're going to underline this, so it's going to be customer ID. If you look in the description over here, can you see that it's how it says it wants to have the first name? Make sure you just take the underline off. First name, surname. I think it was the telephone number as well. So phone number, like that. Okay. Then the next one is we need the booking ID. This also needs to be underlined, so make sure that we underline that, booking ID. Okay, so then we've got that, and then we've got showing ID. Make sure we take that off. Showing ID. And customer ID, which is going to link all of that together. And then finally we need to have like a booked seat, something like that. For the last table, which is we're gonna use the composite primary key on this one to have a fully normalized database similar to the seat up here. So then we're gonna have booking ID. Make sure you spell, if you've used certain case, it needs to be exactly the same in all of these. Booking ID, seat number. And I was thinking screen ID might be quite a good one to include in there as well, because then that will attach obviously the screen to it, and then you've got the links between all of them. So in here, what we've got is it's asking us to describe an issue that could arise if we delete everything from there, and this is all to do with referential integrity. It could be a problem as if we delete values and it tries to reference non-existent values. I'll explain what this means in a sec. Existent values. This causes referential integrity issues because there could already be bookings for that date. Okay, so referential integrity is this idea that in a database, this statement is that you can't reference non-existent values. What that essentially means is if we create a inconsistency in the database where let's say that I've got something about cars, okay? So if we take an example of cars, if I have the license plate as the primary key and I'm linking it with a foreign key, and what I do is I accidentally either delete or I change one of the license plates to be slightly different. Maybe I put an extra number in there or something like that. It doesn't exist. So that causes an inconsistency in the database, and it really doesn't like that, and it will give you an error. Okay, we talk about this a lot. I'll put a little link in the description to our online groups, which you can find out some more information about that, and it helps to support the channel. If you like these videos, check them out, see if there's something that can be of use to you. But yeah, we discuss all of these things, and you can suggest topics and stuff that you can go through in that. The last little part of question 5. So what we've got is we've got a booking system is going to use CRUD and REST. So it's asking us about URLs and how this is used in this case. So URLs are used as a resource for these. It talks about the process of, it shows how REST enables CRUD to be mapped to the database. So that's going to be B in that one. And then finally we've got JSON is used to encode datasets when they are passed between the server and the booking application. Figure 6 shows this. So we've got JSON, and it's saying, why is this better than using an XML file? It's more compact is a JSON. And the other one is easier for humans to understand. If you compare JSON to XML, XML is quite verbose. It's got like there's a lot of stuff to it. So have a little look at the differences between those two. Okay, so what we've got here is we've got some mantises, an exponent, we've got floating point, and it's calculate the decimal value in this. So what we're going to do is, first of all, we need to work out which of the mantissa and the exponent are negative. So with the exponent there, that one is negative. So we need to convert this into positive. So we go to our first one and we find that one. Everything at it and before it stays the same. It's the first one, so that's going to stay the same. Then everything after it is flipped. So that's going to give us 1, 2. So that's going to give us -3. Okay. Now, with this one, we don't have to do anything for it, but this is a negative. So essentially, this number is going to have to get smaller. So I'm going to add in the number of zeros that my exponent is. So it's 3 zeros. And then I just move the decimal point. I'm going to go 1, 2, 3. Redraw my number. I could do obviously more, but I'm just going to stop there. Now, you have got your calculator. So you can use that. You can also actually use fractions in this as well. So half, quarter, eighth, 16th, 32, 64. And then adding fractions together, what we've got there is that's going to be, so 8. So that's going to be 8 over 64 is an eighth. 4 over 16 is going to be that. 1 over 16, so you have all of those, sorry, that should be 64. You have to make all of the denominators the same before you can add them all up. And as you can see there, that's going to give us 13 over 64. And if you needed to, you can just use the calculator to help you out, where you just put 13 over 64, which will give you the decimal. Does it say, so yeah, that we've got 0.2033125. It says write the normalized floating point representation of the decimal value minus 23.25. So first of all, the steps in this one here is we're just going to write out the numbers. So we're going to do 64, 32. So say how many, it's got the number of bits there, 16, 8, 4, 2, 1, and then that's going to be 0.5 and then 0.25 there. Put in a couple of extra ones there, but that's fine. So we're just going to do 23 just to start with. So we're going to go 1. So 23 is going to be 16 plus 4, like that. And then that's going to be like so. So then that's going to be 23.25 as a positive number. Then what we have to do is we have to 2's complement this. So then I'm going to go, because it's negative, so we find our first one, everything at it and before it stays the same, everything after it is flipped. 1, 0, 0, 0, 1, 0, 1. The decimal point is between these two numbers here. Now for a negative number, the decimal point needs to go between the furthest left 1, 0. So what we're going to do is we're going to move the decimal point to there. So we're going to go 1, 2, 3, 4, 5. So the exponent is going to be 5, 0, 1, 0, 1, because that's 1 and that's 4, so that equals 5. Then you just draw the number in there, making sure you do the correct number of bits. So 0, 1, 0, 0, 0, 1, 1. Going through the next one, so it says on each row of the table state the type of error that has occurred in the situation below. Calculation is performed and the result of the calculation is so close to 0 that the number is stored as 0. This is what's called underflow, which is the opposite of overflow. The calculation is performed and the result of the calculation is too large to fit into that, so that's overflow. And then a decimal value is converted to floating point, but it cannot be represented exactly in the available number of bits. So then that's just going to be a rounding error. Okay, so we've got here, so it says, explain how the floating point representation used in question parts 6.1 and 6.2 can be modified to represent the numbers more precisely without changing the total number of bits. So how it works is with the mantissa and the exponent, the mantissa makes it more precise, the exponent is the one that increases the range of numbers that we can represent. The difficulty in this one is it's asking us not to change the number of bits though. So what we would do is we would take bits from the exponent and put them on the mantissa. Okay, so question 8. So we've got a supermarket chain uses a system which stores details of all of the products that it sells and sales that it makes. The data that the supermarket stores is big data. Two characteristics of big data are volume of data, means it's too big to fit on a single server, and the data comes in a variety of forms. Describe the third characteristic of big data. So this is all to do with high velocity, so that the data comes in at a very high velocity. In the mark scheme, they do not give you a mark if you don't imply that there's a lot of data coming in, so you have to add in that extra bit of like very high. If you just say velocity, they said that that's not enough. So look for those little tricks in there with the mark scheme if they're just saying to you things like, you know, have a look, and if it has a little NE, that means not enough. So just be really careful on that. The graph schema in figure 8 represents part of a fact-based model of the data set that the supermarket built. So we've got all of this information here, and we're going to modify the graph schema in figure 8 to represent the following additional facts. So the Bath store sells chocolate biscuits. So what we have to do here is we're going to create the link between them. And then what we're going to do is we have to put what it says, so it sells. So can you see here how with each of these links, what we've got is what it does. So we're going to put cells in there. We then move on to the next one, which there are 20 individual biscuits in the packet of ice biscuits. So we've got ice biscuits, and each packet costs £1.50. So what we're going to do, actually no, because this is to do with the product, it's actually going to be a dashed line in that one there. Nearly made a little mistake there. And this is going to be rectangular because this is going to be information about the product. So I just have to draw a little rectangle there. In there, this won't quite fit, but essentially what we need to do is we're going to put, what was it? It was going to be, so a quantity. And then what we're going to do is made it a little bit bigger now so that you can see it. Okay, so what we've got to do is, so with this part here, so the 20 individual biscuits. So for that one there, we need to put in there how much it's going to come in and how much it's going to cost. So we can put cost, and then that's going to be £1.50. This is going to be a dotted line because this is almost like an attribute of the product. So you put like a dotted line. Sorry, it's not that easy to do it on here. And then we're going to put another one in here. Another rectangle. I'll try and make this one a little bit bigger. And then this is going to have almost like the quantity. So quantity. is going to be the, it's going to go in packs of 20. And again, that's going to be another dotted line there, like that. Okay. Then we go into the final point, which says both chocolate biscuits and ice biscuits are made by the company Delicious Snacks. So we're going to go for an oval for Delicious Snacks. Company, colon, and then we're just going to put Delicious Snacks. I can't spell delicious. Delicious Snacks. Try and make that a little bit smaller so that actually fits in there. There we go. Okay, and then what is it? And the company employs 75 employees. So again, we're going to do a little rectangle for that one. Employees, 75. Okay, and then that's going to be a dotted line going between there and there. Okay, and then we need strong, so when it's not almost like a little attribute of this, what we need to do is we need to make sure that there's a strong line going from one to the other. So that is going to be, oh, it's also got cake bars, which I'll add that in a second as well. So there's going to be a line going to there. And what we're going to do is we're going to put makes in there. So that's going to be makes. We're going to draw an oval. That's not an oval. We're going to draw an oval for cake bars. I'm going to go product. Cake bars. And again, a strong line, no gaps in between them. And then that's going to be makes. Okay, and that's it all completed there. Question here, what we've got is we've got we need to describe two features of functional programming. And what we can say is for these ones, so there's a couple of buzzwords that we can use in this, which is immutable data structures. Now, immutable data structure, so the keyword immutable there is means that not changing. Okay, so when something we cannot change it, another example of this would be, for example, like a tuple is an immutable data structure. A constant is an immutable data structure. It means that it doesn't change. A mutable, which is the inverse of this, is where something can change, like a variable. A list as well is another example of this. The other thing as well with these ones is statelessness, which essentially means that the states aren't going to be interfering with any other parts of the program. So that's what it means by statelessness. Is like the states don't cause any unneeded effects on anything. Okay, so for this question here, what we have to do is we have to do some logic gates. So we've got the inputs, which are just your standard truth table, and then if we look at the outputs, this is what I'd be looking for. To get full marks, we're going to use two gates exactly. So the way that we do this is if we look at C, that's an AND gate. So what I'm going to do is I'm going to put A up to here, and which looks like a D, and that's going to go for the output of C. Now for the next one, if we look here, that's a XOR gate. So we're going to get a connection down from the A there. We're going to move over here. We do an OR. Remember with the XOR, it's like that. And that's going to finish up on D. Explain the purpose of the circuit that you have drawn that produces the output in table 4. What that's going to be is that's going to be a half adder, and it's two. What its job is to do is to add two bits together, which if you actually have a little look, you'll see this, because it gives us the output of, with binary addition, 0 plus 1 equals 1. 1 plus 0 is 1. 1 plus 1 is 0, carry the 1. So that's how it kind of works in that particular way. This is the C being the carry bit there. Okay, for the next question, what we have to do is apply some Boolean algebra rules to this. I've done the first stage because it takes me a little while to set it up on here. So what we've done is we've done De Morgan's law. De Morgan's law here is how we've managed to change this. Okay, so what we've done is not B and C is the same as not B or not C. And we could swap that over there. We can then actually do De Morgan's law again. So if we do De Morgan's law again, this will allow us to get the A out of here. Okay, so what will happen is, if we treat these as two single entities, A or B or C, what this will simplify to is A and. It will actually also take off a number of the nots as well. We have to have it on the C over here though. The reason that we have it on the C over there is because, can you see that we've got three lines? The others we've got two, so we can remove those. And that's going to be the equivalent on there. Once we've done that, we can unlock this bracket here. And we can take the bracket out, which is going to give us that because B and A. So if you almost do a little bit of expanding the brackets on that one. And then we're going to do that again, but with B and C. Just like if you remember back to maths, it's been a little while in maths, where you kind of do like expanding brackets in that. Now the tricky part on this one is we have to do B and A together because it's got an and there. So what this is going to look like is B and A and B, and then it's or B and A and not C, because we have to apply it to both of the values in there. Once we've got both of the values in there, as you can see, what will happen is we can actually start now working with it and applying some of the other De Morgan's laws and the other Boolean algebra ways of simplifying this. Because this is one statement, we can actually do the rule which is, so it's going to be B and B simplifies down to just B. So we can take out one of the B's there, which that kind of helps everything out. The more you do of these, the easier it gets to notice the patterns. Then what we can do is we can actually apply the absorption rule on this one. The absorption rule, just so that you know, it applies a little bit like this, where you've got a gate, like an OR gate, and then you've got X and Y, or it works in this way, which is, say you've got X out there and then you've got X or Y. Now in this case, what we've got is B and A, which that sometimes confuses people that we've got both of those together. We've got the OR, and then we've got the opposite gate over there, can you see? So we're treating the B and A. I think that's the thing that confuses a lot of people, is so you treat those as a single entity, which they're the same. So that would be like X and X there. And then what you can do is then the C gets absorbed, so that then you're left with essentially just one of those. So it's just going to simplify down to just B and A. Now, because these are both ands, what you can do is you can do the opposite of expansion on these, which is factorization. So then that would give us, I'm going to write this in a new one, so it's going to be A, and then you've got B, or, and then not B. I'll just put a little line over the top of that. And then what you've got after that is, then if you do the rule, which is the OR rule, which is going to be, if you've got like X or not X, that simplifies to 1. Because if you think about that, if whatever X is, so if X is 0 and if and then if we've got not x, which is going to be 1, because they have to be one or the other. With an OR gate, we only need 1 for it to be true overall. So that actually would simplify to a 1, no matter which one it is. So then that would just be A, and then it's just going to simplify to 1. And then the rule for A and 1, well, in an AND gate, if we think about how that works, an AND gate is going to work if it's going to work, both of them have to be true for it to be true overall. So if A is 0, it's going to be 0. If A is 1, it's going to be 1. It's going to simplify to A. Okay, for the next one, what we've got to do is we've got to go for the asynchronous data transmission, and we're sending a 7-bit, it's sending over 7-bit ASCII character codes, and it's asynchronous, okay? So we've got a start bit here. So that's going to be the start bit. We've got the parity bit, which is going to be here. So that's the parity bit. We've got the 7 bits for the ASCII code. And then we've got the stop bit here, which is normally a 0 to signify that the transmission's ended. So that's going to be stop. Okay. So we've got the 1 and it should be kind of 1 and 0. So we can ignore the first one. And what this question here is actually asking us to do is to work out which patterns are valid. So what we're looking for is within the start and stop, which should be a 1 and a 0. What we're looking for is an even number of bits, because it says it's an even number of bits. So if we count them here, I mean, it doesn't work because there's a 1 there, so we can kind of skip this one. So let's have a look. 1, 2, 3, 4, 5. So that doesn't work because it's odd. 1. Wow, there's not a 1 there, so that doesn't work. We've got a start bit. Okay, so this works. 1, 2, 3, 4, and there's a 0 at the end there. So we've got 4, so that's good. And then we've got here, we've got start and stop. Got the parity bit. So we've got 2 there, so that works as well. So the answer is going to be 2. So 4 and 5 work perfectly there. Okay, for the next one, what we've got to do is we've got to go for the asynchronous data transmission, and we're sending a 7-bit, it's sending over 7-bit ASCII character codes, and it's asynchronous, okay? So we've got a start bit here. So that's going to be the start bit. We've got the parity bit, which is going to be here. So that's the parity bit. We've got the 7 bits for the ASCII code, and then we've got the stop bit here, which is normally a 0 to signify that the transmission's ended. So that's going to be stop. Okay, so we've got the 1 and it should be kind of 1 and 0, so we can ignore the first one. And what this question here is actually asking us to do is to work out which patterns are valid. So what we're looking for is within the start and stop, which should be a 1 and a 0. What we're looking for is an even number of bits, because it says it's an even number of bits. So if we count them here, I mean, it doesn't work because there's a 1 there, so we can kind of skip this one. So let's have a look. 1, 2, 3, 4, 5. So that doesn't work because it's odd. 1. Wow, there's not a 1 there, so that doesn't work. We've got a start bit. Okay, so this works. 1, 2, 3, 4, and there's a 0 at the end there. So we've got 4, so that's good. And then we've got here, we've got start and stop, got the parity bit. So we've got 2 there, so that works as well. So the answer is going to be 2. So 4 and 5 work perfectly there. Now, an alternative way of an alternative data communication uses synchronized data transmission. Describe what synchronous data transmission is. It's where the receiver, so buzzwords receiver and sender computers send data with a synchronized clock. So they make sure that they both send it essentially, or sending and receiving, and they both make sure that they're doing that at the same time because their clocks are the same. And that's a way of checking, because then they can check the time when things are sent between them. So that's the buzzwords there being synchronized clock is that one there to get the mark, because there's only 1 mark. Describe one limitation that uses parity bits for managing errors. So technically, if the bits flip, it will catch it if it's an odd number, but it could flip the bits to an even number, and it, e.g. 4 to 6, and it wouldn't catch the error then, because if it's looking for an even parity, it's like, yeah, that's good, but it was meant to be 4 and it's changed it. Shade 1 lozenge to indicate which of the lines of the graph in figure 10 show the correct relationship between them, and that's going to be this one, line A. It's directly proportional, so if the bandwidth gets higher, the bit rate also has to get higher. Okay, so we've got a bit of networks on this. So what we're going to do is we've got an email being sent from user A to user B using computer B, on computer B, sorry, and describe the role that will be played by the transport layer in the TCP/IP protocol stack. So in this one here, so the transport layer is just underneath the application layer, and essentially it's going to take the data from the application layer, and in this one, because it's 3 marks, we need to make 3 solid points. So what we're going to say is it's going to split the data up, ready to be sent. At this layer, this is where we put the port numbers on as well, so put port number on packets. And also this is where error checks are added to data. Okay, so those are the 3 points. Because this is the process of it sending it, so it's getting it ready, so it's putting error checks on there so that when it sends it over and computer B receives it, then it can do the error checks. It also needs to make sure that it's being sent to the correct port, and also needs to make sure the data's sent, and then it passes it down to the internet or network layer, depending on what you've been told as it's called. Internet and network is a synonym for each other. Let me just move this down. Whilst being transported across the internet, the email data passes through a number of routers and 1 gateway. Describe the added functionality of a gateway beyond that of a router. So sometimes routers have gateways on them, and this is where it's essentially allowing different protocols to communicate with each other. So it's like data with different protocols allows them to communicate. So it kind of like there's a term which is like protocol. I think it's protocol conversion, where it just allows essentially different protocols to communicate with each other. State the name and purpose of 2 application layer protocols that can be used to transfer the email from A to B. Each protocol must have a different purpose. Okay, so first one that we're going to have is SMTP, and the purpose is to send the data or send the email to the mail server. Now, if we think about it, we can also use the receiving ones, because it just says state the name and the purpose of 2 application layer protocols that will be used to transfer the email from computer A to computer B. Now, that makes me think of, like, I can only use ones which are like that the computer A is using, but you can actually also use the ones in computer B, because that's still part of the process of getting it over. So you could use like POP3, IMAP, which are to do with receiving the email from the mail server. Remember, POP3 is the one where it will delete it from the mail server once you view it, and you can only view it on one device. The other one I would go for is HTTPS. As I said, you could use the other ones; they're absolutely fine. But it's I thought this was quite a nice one, where it's like it allows you to get onto web browser and then go to mail server to send email or receive it, you know, in that one there. So I just thought that was quite a nice one there. Last little part on here, it says email servers involved in transmission of emails use well-known ports. Explain what is known by what a well-known port is and why an email server must use one. So a well-known port is a port that has a specific purpose. So for quite a lot of different tasks on when you're connecting, using different protocols, they have specific ports, and the reason that we're using those ones is that it allows the computer to know that the port is being used for the purpose it is designed for, and also helps with security issues. So when we have a port, so with the port, essentially we need to make sure that we're sending all of the data to that correct place, because that's what it's intended for. So if you're sending various data, if you're sending files, if you're emailing, it's going to have a port that has a specific purpose, and that helps the computer know that it's being used, and that's what it should be being used for. And it also knows that if we're getting weird connections from different IP addresses, it can also really help with different security issues in there as well. So it helps in that regard as well. Okay, so this is all to do with essentially how do we send the data over and from one to another using asymmetric encryption, and it's also talking about digital signatures. It's talking about how does it get from A to B, and computer A to B. What's the process? It's asking for 6 marks, so I think we should do 3 for sending it, 3 for receiving it. Let's talk about that. So this is all to do with creating a hash by applying an algorithm to generate this on the message being sent to give you a digital signature. We use the private key of A on the digital signature and attach this to the message. Okay, so that's 3 points all sorted for that. Then what we're going to do is the other side of so when we receive it. So when we receive the data, we recalculate the hash using the same algorithm, and we compare the values. We compare the values against the one that was sent. If they are the same, we know that the values that it is authentic. If not, if not, we know that this has not come from the intended sender. So if those values are different, that's when you know that you've got an issue. And there's plenty of points there. We've made, I think, 7 points there. You can also talk about, obviously, the public keys. You can talk about all sorts in that. But that's enough points to get full marks on this. Okay, last question, and then we're all done. Just the last little thing. I'll put some things in the chat and the description. If you want to reach out, help support the channel, I'll put some links to group lessons, individual lessons, links to the website, online courses. It really helps because these videos do take a very long time to make. But obviously I want to help you guys out. So, if you can help support, that would be really appreciated. But if not, please still get enjoy the free content. So anyway, with functions, what's going to happen with this is it's going to call itself recursively, okay? And what we need to do is we need to get to the point where we unwind, and then we can actually work out what's going on here. And that little X, the little colon part, is how it takes the front value off the front of the list each time. So what this will do is so the 4 gets taken off, and then it's going to be that. And then the 2 is going to get taken off, which is going to give us that. 4 gets taken off. Sorry, the 5 gets taken off, which is just going to leave us with 3. And then finally, it's just going to be an empty list. Now, when it gets to an empty list, it's going to unwind there. So there isn't going to be anything. If we run this, which obviously what X is, it's going to be like 0 plus. So it will do 2 times the function call, sorry. So 2 times 0, and then it's just going to give us 0 for the first one. Then what it's then going to do is it's going to do 2 times 0, and then plus 3. So 3 is going to take that position, and then the function call before. So 0. So we've got 2 times 0, which is 0, plus 3, which that's going to be 3. 5 is going to take the place of this, and then we've got the function call before of 3. So 5 plus 2 times 3. So that's going to give us, so that's 6. So 5 plus 6, because 2 times the function call, a little bit confusing there. So that the function call, remember, so the value returned there is 3. So then that's going to be 5 plus 6, which is going to be 11. So now we're going to take the 11 on. We're going to put 2. So 2 is going to go here. 2 times 11 equals 22, plus the 2 is going to give me 24. Nearly said 22, 24. And then we're going to take the 24 as the function call. So we're going to, and then we're going to put 4 there. So 4 plus 2 times 24, which is 48. So 48 plus 4 is going to give us 52. And then the last little thing is it says all the values are passed in function z as the argument are members of a set of integers. Shade one lozenge to indicate the codomain of the function. Now this is to do with all of the values that we're using. So what could all of the values be in irrational numbers, natural numbers, and all this? Every single one of these is, so they're not irrational numbers. They're all positive, which is great. And then, so what we need to do is this is going to be the set. They're going to be a set of integers, yeah, because that's just what they all are. Okay. Hope that was useful, people. As I said, you know, it does take a really long time to do these videos. You know, please, you know, share it, you know, and get it out there. I'm trying to help as many people as possible. And have a look in the description if there's something that we can do to help you out. Thank you very much. Hope that was useful.